Hello there, and welcome to All About Earth, a quiet corner of wonder where we let time stretch, where science doesn't rush, and where imagination gets to breathe. Wherever you are, curled under a blanket, resting after a long day, or watching the first hints of dawn spill through the window, I'm glad you're here. Tonight, we're not visiting the age of dinosaurs, nor the rise of forests or oceans filled with color. No, we're going much further back, to a world so young, so wild, that it might not even recognize itself as Earth yet. A world about 4.6 billion years ago, when our planet was quite literally alien to life. Imagine stepping outside, if you could survive it, and seeing a horizon of molten rock. The air isn't really air at all. It's a haze of carbon dioxide, methane, and ammonia, thick as soup and toxic enough to melt metal. Volcanoes roar without rest, spraying molten fountains high into skies, the color of rust and fire. Lightning forks through chemical clouds, each flash igniting new reactions in the chaos. The ground shudders beneath your feet if feet were even a thing that could exist. The crust is young, cracked, still cooling from the furnace that once was space dust and collision. Every few hours, another asteroid arrives, some small, others mountain-sized, slamming into the surface with enough force to boil oceans that haven't even formed yet. And yet, beneath all this destruction, something extraordinary is happening. The planet is settling. Its molten skin is beginning to harden. The wild rain of rock from the heavens is slowing, like the final drops of a storm. Steam thickens into clouds. The first rains fall, not gentle showers, but acid downpours, hissing as they strike the hot surface. They cool it, little by little, drop by drop, century by century. Those early rains carve channels in the newborn crust. They gather in shallow basins, creating the first proto-oceans, strange metallic waters that bubble and steam under an unfiltered sun. You wouldn't dare dip a toe in. The chemistry is harsh, almost alien. But those chaotic seas are the beginning of everything that would one day swim, crawl, grow. If you could stand there, just for a moment, what would you feel? The heat? The danger? Or maybe hidden beneath the noise and fire, a kind of promise, a sense that the earth in all her fury was already rehearsing for something gentler, something that could host life, because even in this storm of molten rock and poisonous skies, the ingredients of the future are being stirred together. Carbon, hydrogen, oxygen, nitrogen, sulfur, atoms waiting for their cue. It's a messy, unpredictable chemistry set, but one day, long after the last asteroid fades from the sky, those elements will join hands to form something miraculous. For now, though, the Earth is still too wild, too young, too dangerous to be called home. This is the chapter before the beginning, the era when the planet was beautiful in a terrible way, when survival was impossible but creation was inevitable. So, as you listen, imagine yourself standing on that alien shore, where the ground glows faintly with heat and the sky is alive with fire. There's no life to hear the thunder, no eyes to watch the waves, but you, from billions of years in the future, can witness it in your mind. Close your eyes, take a slow breath, and picture it, a planet blazing in solitude, unaware that one day it would cool, bloom, and sing with life. If this vision stirs something in you, curiosity, awe, a tiny spark of what if, you can share it below. Tap like, leave a thought, or simply stay with the wonder for a while. Because this is just the beginning of the story, the time when Earth was not yet for us, but was already becoming something miraculous. And soon we'll watch it change. We'll see how chaos began to calm, how stone met water, and how a hostile world started to prepare for life's arrival. But that's for next time. For now, rest your thoughts in deep time. The fire will fade, the oceans will rise. And from this storm, one day, life will begin to whisper. From the spinning dust of ancient stars, Earth was born, not gently but violently, in a cosmic storm of fire and gravity. Picture the early solar system, not the calm clockwork ballet we see today, but a wild celestial construction site. The newborn sun blazed at the center, still wrapping itself in ribbons, gas, and magnetic tantrums, while around it swirled a chaotic disk of debris, dust grains, ice shards, fragments of metal, all tumbling, colliding, and clumping together in the gravity-fueled frenzy that would one day become planets. In this glowing ring of matter, chaos was the rule, and collisions were the language of creation. Tiny grains of silicate dust, leftovers from generations of earlier stars that had lived, burned, and exploded, began to stick together. Static electricity, faint as the whisper between hair and sweater, pulled them into clumps. Those clumps became pebbles, pebbles became boulders, and boulders became planetesimals. Baby worlds, each tugging on its neighbors with invisible threads of gravity. You could think of it as the most dangerous mosh pit in cosmic history. Everything smashed, melted, fused, and started over again. Amid this celestial storm, about 4.6 billion years ago, our planet-to-be began to take shape. Not as a calm blue marble, but as a glowing sphere of molten rock, spinning faster than your mind can comfortably hold. Every impact added energy, and every new piece of matter was like a spark tossed into a forge already roaring. Temperatures soared past 1,000 degrees. The entire surface churned with magma and metal. The Earth was, quite literally, liquid rock in motion. If you were to stand there, assuming you could stand and ignoring the small detail that your atoms would instantly vaporize, it would be like standing on the sun's distant cousin. The air shimmered with heat. The sky, if you could call it that, was thick with dust and glowing debris from endless collisions. Asteroids the size of mountains rained down like angry confetti. Each impact released enough energy to boil entire oceans that hadn't yet formed. It was less a planet and more a foundry. But within this inferno, something miraculous was happening. Order was slowly emerging from chaos. The constant collisions caused heavy elements like iron and nickel to sink toward the center, while lighter materials, silicates, magnesium, aluminum, floated upward. Earth was beginning to separate into layers, like a cosmic parfait. At the heart, the iron core formed, dense, molten, and alive with motion. Around it, the mantle swirled in convection currents of half-melted rock, like an ocean of fire. Above that, a thin crust began to cool, crack, and reform with every new bombardment. The process wasn't peaceful. Gravity kept pulling more material inward, compressing the young planet's interior until it glowed with internal heat. Every atom that fell to Earth's surface brought not just mass, but energy, kinetic energy that converted to heat on impact. Add to that the decay of radioactive elements like uranium, thorium, and potassium, and you get a self-heating engine that made sure Earth stayed molten long after the bombardment eased. It's strange to think that our planet's solid iron heart, the same core that now generates the magnetic field protecting us from cosmic radiation, was born out of violence. As iron sank toward the center, it carried with it vast amounts of energy. The motion of that liquid metal would one day power the planet's magnetic shield, but for now, it simply made the young Earth rumble with deep metallic thunder. Meanwhile, the surface was a constant battlefield. Asteroids and protoplanets smashed together in collisions, so powerful they could vaporize continents. One of them, about the size of Mars, is thought to have struck Earth in a glancing blow. The debris from that impact was flung into orbit and later coalesced into our moon. The two worlds, Earth and its new companion, glowed like twin embers in the young solar system, locked together by gravity and destiny. The moon's pull would slow Earth's rotation and steady its tilt, but at this stage it merely circled a planet that was still a cosmic cauldron. Let's pause there for a breath. Though in this world, breathing would be a bad idea. The early atmosphere wasn't the friendly mix of nitrogen and oxygen we know today. It was more like the exhaust from a million volcanoes. The original gases, mostly hydrogen and helium captured from the solar nebula, were light, fast, and hopelessly uncommitted. The newborn sun, still fierce and volatile, blasted them away with intense solar wind. Those fragile gases fled into space, leaving behind a bare, seething planet. What replaced them was a thick, toxic haze born of the Earth's own fury. Volcanoes, endless and enormous, belched out carbon dioxide, water vapor, methane, and ammonia. The skies turned copper red, then black, then sulphurous yellow as new gases joined the mix. Lightning forked through the clouds, igniting chemical storms that would one day sow the seeds of life. But for now, they only made the inferno worse. Rain, if it could fall at all, would have boiled before it touched the ground. Imagine droplets of acid sizzling on molten stone, a sky that burned, and a ground that smoked. And yet, in a strange way, all of this chaos was necessary. The constant outgassing from volcanoes began to thicken the atmosphere, trapping heat and keeping the planet from cooling too quickly. Those gases carried the water vapor that would, much later, condense into the first oceans. The same violent chemistry that made Earth unlivable was also writing the recipe for future habitability. It's as though the planet had to shout before it could learn to whisper. Meanwhile, the young sun watched on, glowing brighter with each million years. Its radiation stripped away what little hydrogen and helium remained, but its warmth kept the Earth's molten heart alive. The planet spun rapidly, completing a day in barely 6 hours, while its surface churned and cracked like a slow explosion. The magnetic field, faint but forming, began to stir deep inside, a kind of invisible heartbeat pulsing beneath the chaos. The surface itself was in constant motion. Rivers of lava flowed like liquid lightning. Vast regions of molten basalt cooled, solidified, and were instantly torn apart again by fresh impacts. Imagine a world that never stopped erupting, a global forge constantly breaking and remaking its own crust. No oceans yet, no continents, no sky-blue serenity, only a world glowing red, wrapped in steam and shadow, sculpted by violence. If there were sounds, they would be deep and endless. The roar of impacts, the hiss of vaporized rock, the crackle of lightning across skies that never darkened. If there were smells, they would be sulfur, metal, ozone, sharp and alien. If there were light, it would come not just from the sun, but from the earth itself, glowing like a coal in the cosmic dark. And through it all, gravity held firm. The same force that had drawn dust grains together now kept this furious young planet from flying apart. Every new impact added mass and energy, but also shape and identity. The solar system was still dangerous, but Earth was learning endurance. It was gathering the strength that would one day allow it to cradle oceans, mountains, and life. Eventually, after countless collisions and eons of cooling, the bombardment slowed. The rain of rock and fire began to ease. The molten seas solidified into a rough, scarred crust. Volcanoes still erupted, but in their smoke rose the first traces of the gases that would become air. The surface, though still unimaginably hot, began to harden, an uneasy calm settling over a world that had spent its childhood on fire. At this point, Earth was no paradise. It was closer to a furnace than a garden. The heat radiating from below made the ground shimmer. The air was thick enough to press against you like a weight, filled with sulfur, carbon and steam. But if you could hover just above it, you might have noticed something changing. The light was shifting. The planet was no longer just red-hot chaos. Patches of darker crust glimmered among the molten flow. The first hints of blue scattered sunlight through volcanic haze flickered at the edges of the sky. The Earth, for the first time, was beginning to look like a planet. It's tempting to imagine that the planet knew what it was becoming. As if deep within the magma, it whispered, "I'm almost ready." The truth, of course, is that there was no plan, no consciousness, just physics, chemistry, and time. And yet, standing here billions of years later, you can't help but feel that there was something almost poetic about the process. The same iron that now guides compasses was once liquid fire at the planet's core. The same rock beneath your feet once flowed like water. The same carbon that forms your cells was forged in that early atmosphere, released by volcanoes older than the moon. Earth's birth was not a gentle beginning. It was an ordeal. But it was also a kind of cosmic art. From dust and flame, from collisions and chaos, came structure, balance, and potential. The solar system's debris field had given rise to a world capable of complexity, beauty, and eventually consciousness. When you look at the planet today, calm oceans, green forests, clouds drifting lazily across the sky, it's almost impossible to imagine that it began as a sphere of liquid fire. Yet, deep down, that heat still burns. The mantle still convects. The core still spins. The planet still hums with the ancient energy of its birth. So the next time you feel solid ground beneath your feet, remember that ground was once stardust, then molten chaos, then rock tempered by billions of years of patience. Earth was forged in collisions, sculpted by gravity, and cooled by time. It was for a while too hot to touch, too wild to inhabit. But in that fiery crucible, it found its form. And somewhere in the shimmering heat of that long-ago world, the seeds of everything we know, oceans, continents, clouds, and life were waiting. Not yet visible, not yet ready, but already inevitable. From dust, fire, and fury came the home we now call Earth. And though the flames have faded, the story of that birth still burns quietly beneath us, deep in the iron heart of the world. Welcome to the Hadean Earth's earliest chapter, and easily its loudest, hottest, most dramatic. If the planet had a childhood, this was the tantrum. Between about 4.6 and 4 billion years ago, our world was not the blue marble you know, not even close. It was more like a cosmic foundry, a world of fire, thunder, and molten stone, where continents were a rumor and oceans a dream. Imagine trying to land here. The ground would eat your spaceship, the air would dissolve your lungs, and the sky would glow with perpetual fire. You'd step out, take one look, and think, ah, so this is what hell was modelled after. The name fits. Hadean comes from Hades, the Greek underworld, and for once, scientists and poets agreed. It was an age of chaos, an era when Earth itself was still deciding what it wanted to be, and the process was anything but gentle. Picture a planet covered in magma oceans, hundreds of kilometers deep, their surfaces heaving like slow, angry tides. Lava fountains burst through cracks in the crust, only to be obliterated by incoming asteroids the size of cities. Mountains didn't last more than a few days before melting back into glowing rivers of rock. If you could hover safely above the surface, you'd see a world still half liquid, half smoke, wrapped in a shimmering red haze that made it look more like a small, angry star than a planet. Everywhere you looked, something was exploding. The solar system itself was still young and untidy, like a toddler with too many toys and no sense of consequence. Leftover planetesimals, comets, and proto-moons hurled themselves through space, colliding with whatever got in their way. For Earth, that meant a steady bombardment of rock, metal, and ice. Each impact unleashed energy beyond comprehension. The largest could vaporize oceans that hadn't even had time to form, or punch new craters so deep they nearly cracked the crust in half. These collisions weren't rare. They happened every few thousand years, a blink in geological time. You could call it the heavy bombardment, but it was more like the universe's most violent fireworks show. The air, if we dare call it that, was dense, choking, and utterly alien. Forget blue skies. The Hadean atmosphere was a boiling soup of carbon dioxide, nitrogen, sulfur dioxide, and water vapor, with occasional sprinkles of methane and ammonia. It was thick enough to crush you, hot enough to melt metal, and entirely unbreathable. The sun, faint through the haze, was a dull orange disk, and its rays scattered into an eerie perpetual twilight. Lightning ripped constantly through the clouds, illuminating curtains of volcanic smoke in brilliant flashes. Each bolt set off new chemical reactions in the atmosphere, splitting molecules apart and building strange new ones in their place. It was as if the sky itself were experimenting, fumbling toward the chemistry that would someday make life possible. The surface below, though, was not in any mood for subtlety. Vast seas of molten rock stretched from horizon to horizon, rolling like waves in slow motion. These magma oceans weren't poetic exaggerations. They were literal oceans of silicate melt, hundreds of kilometers deep. Convection currents churned within them, dragging heat outward, swallowing fragments of solid rock and vomiting them back up as glowing fountains. Over time, as the planet radiated its heat into space, the outer layers began to cool and solidify, briefly. But just when a crust managed to form, another impact would arrive and shatter it, returning everything to chaos. It was the planetary equivalent of trying to bake a cake in an oven that kept exploding. You might wonder what this looked like from orbit. Imagine a half-lit world glowing red and orange, its surface veined with rivers of fire, vast plumes of molten rock arced into the air from impact sites, raining down as incandescent storms. Around it all, clouds of vaporized rock shimmered, condensing into glassy droplets that fell back to the surface like metallic rain. The young moon, born not long before from one catastrophic collision, hung close in the sky, so close that it looked enormous, 20 times larger than it appears today. Tides weren't gentle back then. They were catastrophic surges of molten material pulled back and forth by the moon's gravity. Earth and moon were locked in a gravitational dance of heat and violence, spinning faster and pulling tighter with each passing day. It's hard to imagine that this inferno would ever calm down. And yet, beneath the noise, order was slowly, almost secretly, beginning to emerge. Deep inside the planet, the heavy elements, iron, nickel, and their metallic kin, were still sinking toward the center, forming the dense core that would later give Earth its magnetic field. Above that, the mantle continued to churn, circulating heat like a great red heartbeat. The process was brutal but crucial. It allowed the planet to differentiate, to evolve from a uniform ball of rock into a layered, structured world. Out of molten madness came the first signs of planetary architecture. But make no mistake, this was no place for life. Not yet. The temperatures on the surface were well above the boiling point of water. If oceans existed at all, they were fleeting, thin films of vapor that condensed briefly in cooler regions before evaporating again. Some scientists think there may have been tiny islands of solid crust that managed to survive between impacts, but they would have been short-lived, drowned in lava, or shattered by the next collision. The Hadean Earth didn't have weather, not really. It had chemistry, it had energy, it had violence on a planetary scale, and yet, for all its hostility, it was spectacular. Imagine watching the planet from a safe cosmic distance, say from the orbit of Mars. You'd see a glowing marble, its surface flickering like hot coals under a haze of steam. Every few hours, a new impact would flash bright enough to outshine the sun for a moment. Plumes of molten rock and gas would rise, expand, and drift away into the solar wind. Some of that material escaped entirely, spreading dust across the inner solar system. Tiny fragments of what would later become meteorites. Others fell back, coating the Earth in a thin film of glassy minerals. It was as if the planet were forging its own armor, one explosion at a time. At this point, the entire surface was in motion. You couldn't have drawn a map. There were no landmarks, no continents, no fixed seas. The crust was constantly melting, reforming, and being swallowed again. Deep below, radioactive decay kept the mantle roiling like a pot, left boiling too long on the stove. Volcanic eruptions vented superheated gases into the atmosphere, and as those gases cooled, they condensed into strange chemical mists. The planet was still losing its excess heat to space, but slowly, stubbornly, it would take hundreds of millions of years before things even began to resemble stability. We might think of this as a time of destruction, but it was also a time of preparation. The Hadean wasn't just a nightmare, it was a necessary crucible. The intense heat drove chemical reactions that released volatile elements, water, carbon, nitrogen from the planet's interior. Those gases filled the atmosphere and would one day provide the ingredients for rain and oceans. The constant bombardment mixed materials from across the solar system, delivering metals, minerals, and even, perhaps, a few precious molecules of water and organic compounds. Each collision was a catastrophe. Yes, but also a kind of cosmic delivery service. Earth was being stocked with the ingredients of life even if it wasn't ready to use them yet. Still, let's not romanticize it too much. The Hadean was brutal. Temperatures on the surface likely ranged from 100 to 2000 degrees Celsius. The pressure of the thick atmosphere added another layer of oppression. Thunderstorms of molten silicates raged in the upper air. The very rain that fell from the sky could carve glass into rock. In some regions, molten lakes may have cooled just enough to crust over, forming temporary landmasses that glowed faintly from below like hot coals under ash. Step on one if you could, and it would crack and swallow you whole. This was a planet with no mercy, no shade, no place to rest. If Earth had a motto during this age, it would have been something like, "Not yet, but getting there." And yet, through the smoke and the heat, a slow transformation continued. The bombardment that had once been constant began to taper off. The impacts didn't stop. There were still plenty of space rocks eager to make an entrance. But the intervals grew longer, the magma oceans began to cool, and the first stable crustal rocks might have formed tiny fragments of minerals like zircon that still survive today. These crystals, no bigger than a grain of sand, are the oldest evidence we have of the Hadean Earth, tiny time capsules that whisper, I was here when the world was young. It's humbling to think about. Everything we know about this epoch comes from a few scattered minerals and the faintest chemical fingerprints in ancient rocks. The rest we infer, piece together, imagine. But even imagination struggles to capture the scale of it. The heat, the violence, the sheer persistence of creation. This was a world being hammered into existence, sculpted not by gentle winds or flowing rivers, but by collisions, lava and time. Somewhere around 4.1 or 4.0 billion years ago, the curtain began to lift. The planet's surface cooled enough for the first pools of liquid water to form, brief, unstable but real. The atmosphere began to thin slightly as the worst of the volcanic gases were absorbed by the crust and the newly forming oceans. The light from the sun began to reach the surface in golden streaks rather than dim, sulphurous glow. The worst of the bombardment slowed, though not entirely. A few more large impacts still came to leave their marks. But gradually, Earth's heartbeat steadied. The magma seas receded. The crust thickened. The red faded into grey. By the end of the Hadean, the planet had transformed from a molten inferno into something merely hot, unstable, and unpredictable. An improvement, to be sure. Oceans were starting to form, at least in patches. The air was still thick and toxic, but less suffocating. Volcanoes still ruled, but their eruptions were no longer constant. The ground, once fluid, was now mostly solid. It was, finally, a planet that could be seen without flinching. And so the Hadean came to its slow, simmering close. Earth had survived its own violent birth, its molten adolescence, its cosmic tantrums. The scars it bore, the iron core, the layered mantle, the moon in its orbit, were not wounds but memories. They told the story of a world that refused to remain chaos, that turned fire into structure, destruction into foundation. If you could whisper a message to that young Earth, still cooling in the dim light of a newborn sun, maybe you'd say, "You did it. You made it through the storm." The planet, steaming and scarred, might reply with a low volcanic rumble. "Not yet, but I'm getting closer." The Hadean was hell, yes, but it was a necessary hell. Out of its infernal seas came the first crusts, the first rains, the first whispers of stability. It was the time when Earth was too hot to live, but too stubborn to die. A planet learning how to be a world, and though the fires have long since dimmed, every mountain, every ocean, every quiet breeze that touches your skin still carries the echo of that ancient fury, the memory of a time when the Earth itself was molten, magnificent, and utterly alive. The first breath of Earth was not a sigh of life, but a hiss of poison. Imagine standing on the edge of a world newly cooled from fire, rocks still steaming, volcanoes coughing ash into the sky, the ground warm enough to bake stone, and above it all, a thick, churning atmosphere that looked more like the inside of a chemistry experiment than a sky. If Earth could have spoken then, it might have whispered, "Don't breathe yet. Trust me, you're not ready for this." This was a world wrapped in fumes, and that blanket was anything but comforting. The air was dense, soupy and aggressively unpleasant. Instead of oxygen and nitrogen, the cozy mix that sustains our lungs today, it was filled with gases that would have made any modern creature drop on the spot. Methane, ammonia, carbon dioxide, sulfur dioxide, hydrogen sulfide and water vapor. Think of it as a global cocktail of volcano breath and comet residue, shaken and stirred by lightning, and served at a cozy temperature of a few hundred degrees Celsius. Delicious. Volcanoes ruled the skyline. They erupted constantly, vomiting molten rock and great plumes of gas that spread across the horizon like bruises in the sky. Every eruption belched more carbon dioxide and methane into the air, thickening the atmosphere until sunlight itself had to fight to get through. The result was a permanent twilight, a rusty orange haze that turned the world beneath it into a dimly glowing oven. If you looked up, you might not see the sun at all, just a reddish glare behind veils of ash and steam. To a modern visitor, it would have been uninhabitable in every sense. The air was too thick, too hot, too chemically aggressive. There was no ozone layer to block ultraviolet radiation, so deadly rays sliced through the haze and hit the surface like invisible daggers. The planet's early gases weren't just unbreathable, they were actively hostile. Ammonia and hydrogen sulfide would burn your lungs if you somehow had lungs that hadn't already dissolved. Methane would suffocate you by crowding out oxygen that didn't exist. Even carbon dioxide, harmless in small modern doses, was so abundant that it trapped heat like a prison. The greenhouse effect was not a gentle balancing act, it was a planetary stranglehold. And yet, in this toxic stew, something remarkable was happening. Earth was experimenting. Each volcanic plume and lightning storm was a kind of planetary laboratory, a chaotic playground of molecules colliding, splitting, and reassembling in strange new ways. Methane mixed with ammonia, water vapor met ultraviolet light. The energy from solar radiation and volcanic heat drove reactions that built complex organic molecules, amino acids, hydrocarbons, precursors of the chemistry that much later would define life. You could say Earth was cooking, though at this stage the recipe was mostly trial and error. If you could hover safely above the surface, say in a sturdy orb of science fiction glass, you'd see a world both terrifying and beautiful. Clouds of steam and soot billowed up from endless volcanoes, spreading into layers of gas that glowed faintly from the reflected light of molten land below. Bolts of lightning arced through the haze, igniting patches of methane like brief blue-green fireworks. Every flash, every rumble, every chemical spark added another ingredient to the atmosphere's strange brew. This was not the air of life, but it was the air that would someday give life its first chance. But let's not rush to optimism. For the first few 100 million years of Earth's atmosphere, the planet was firmly in the do not inhale category. The air pressure alone might have crushed you. The humidity was so high it would make a rainforest seem arid by comparison. Water vapor hung heavy in the air, condensing into torrential rains that fell onto still cooling rock, only to hiss back into steam the moment they touched down. It rained for millennia without ever forming a stable ocean, a cycle of evaporation and return, a planet caught in its own fever dream. And oh, the smell! Imagine an entire world that smells like 1,000 rotten eggs, mixed with burnt matches, stirred into boiling tar, and served under a dome of thunder. That's the perfume of hydrogen sulfide, courtesy of the endless volcanic exhalations. Carbon dioxide added its invisible weight, pushing heat back toward the surface, while methane, a potent greenhouse gas, sealed the deal, ensuring that Earth stayed hot enough to glow in the dark. The combination was catastrophic for comfort, but perfect for chemistry. You might think a world like this would repel life entirely, and it did for a long while. Modern organisms would have had no chance here. Oxygen, which we now consider essential, was practically non-existent. The few atoms of it that did form were instantly bound into minerals or reacted away. Any living thing that relied on breathing would have been as doomed as a candle in a hurricane. But the absence of oxygen was precisely what made this early atmosphere chemically restless. Without oxygen to stabilize reactions, everything was in flux. Molecules broke apart easily, rearranged themselves constantly, and flirted with new combinations. The air was alive with possibility, even if nothing alive was there to note. At ground level, things were even wilder. The first crust, though solid, still pulsed with heat from below. Lava flows oozed and crackled, releasing plumes of carbon dioxide and sulfur dioxide that mingled with the stormy air. Lightning forked across the sky, driven by the clash of dust and ash particles. Each bolt packed enough energy to split molecules apart, creating radicals, highly reactive fragments that eagerly joined with others to form new compounds. Somewhere in this chaos, simple organic molecules, things like formaldehyde, hydrogen cyanide and methanol began to accumulate. It wasn't life, not yet, but it was the raw alphabet of biochemistry beginning to write its first hesitant letters. Meanwhile, the sun kept blasting the upper atmosphere with ultraviolet light. Without an ozone layer to filter it, UV radiation tore through the gases like scissors, breaking bonds and spawning new ones. The result was a constant chemical churn, a balance between destruction and creation. In a sense, Earth's first atmosphere was an enormous continuous experiment in thermodynamics. It was unstable, reactive, and volatile, but it was also fertile in a strange molecular way. Scientists call this kind of atmosphere reducing, meaning it had more hydrogen than oxygen, and favored the formation of molecules that could hold on to that hydrogen. In practical terms, that meant methane, CH4, ammonia, NH3, and hydrogen sulfide, H2S, were plentiful, while oxygen, carbon monoxide and ozone were essentially absent. The chemistry was primitive but energetic. When Stanley Miller and Harold Urey tried to simulate such conditions in a lab in 1953, using a flask filled with methane, ammonia, water vapor, and sparks of electricity, they found that amino acids, the building blocks of proteins, spontaneously formed. So even though Earth's first breath was deadly, it was also creative. The air was poisoned, but it was dreaming of life. Let's not forget the theatrics of it all. The sky glowed strange colors: copper, crimson, violet, depending on what chemicals were swirling in the air that day. The sun's light scattered through layers of soot and gas, turning sunsets into permanent phenomena. The nights, when they existed, were lit by the glow of volcanoes and the reflected shimmer of lightning on clouds thick as stone. From a cosmic distance, Earth must have looked hauntingly beautiful, a dark sphere wrapped in luminous orange haze, flickering like a live ember against the black. Yet, despite the beauty, the atmosphere was hostile in every measurable way. It trapped heat, blocked light, and coated the planet in a constant fog of chemicals. The surface temperature swung wildly, hot enough to melt lead in some places, cool enough for fleeting rain in others. The winds were heavy and slow, dragging particles of ash across the planet's face like sandpaper. There were no clear skies, no constellations, no starlight reaching the ground. The planet was wrapped in its own exhalation, hidden from the cosmos as it labored through its adolescence. Every once in a while, a comet or asteroid would strike, punching through the atmosphere and throwing up new clouds of vaporized rock. These impacts added new ingredients: ice, carbon compounds, maybe even traces of nitrogen-rich molecules from outer space. The atmosphere grew thicker still, a chemical soup both ancient and alien. Each addition shifted the balance slightly, cooling some regions, heating others, but never enough to make it calm. Over time, however, small changes began to accumulate. The endless volcanic eruptions slowed their tempo, and the planet's interior began to stabilize. The constant rain of asteroids eased. Water vapor, still abundant in the air, began to condense more permanently. As the first long-lived crust formed, some of that water pooled on its surface, cooling the rocks and absorbing gases from the air. The process was gradual, but it marked the beginning of the end for Earth's suffocating haze. The sky, once a thick orange-brown, began to thin ever so slightly. Sunlight, pale and filtered, started to reach the ground. The planet was still toxic, but for the first time, it could begin to cool. Even then, the air would have been unrecognizable to us. Carbon dioxide still dominated, ensuring that the greenhouse effect kept the planet comfortably hot for its ongoing chemistry lessons. Methane added to the warmth, and ammonia continued to swirl through the upper atmosphere. But the sheer density of the air began to drop. The first faint winds, still heavy, still chemical, moved across the surface, stirring dust and vapor. The Earth was breathing more slowly now. It wasn't the breath of life yet, but it was a step closer to calm. It's fascinating to think that this poisonous haze was the foundation upon which everything later depended. The nitrogen that now fills most of our breathable air, it came from those ancient volcanoes. The carbon dioxide that plants use to make oxygen, that too was belched out in the planet's first breath. Even water, the gentle, life-giving liquid, may have come partly from the condensation of that early steam. The air that would one day nourish forests, oceans, and animals began as a death cloud. If you had told that early Earth that its suffocating gases would one day help raise civilizations, it might have laughed or burped volcanically in disbelief. But that's the paradox of planetary evolution. What begins as poison can become promise. The same atmosphere that would have choked any living thing was quietly laying the groundwork for life's chemistry. It was a strange, smelly, and dangerous modem, but a womb nonetheless. By the time millions of years had passed, the atmosphere had shifted into something slightly less hostile, though still far from habitable. The rains finally began to settle into stable pools, and the first oceans, faint, shallow, and warm, started to collect. The steam that once ruled the sky began to fade. Methane and carbon dioxide still filled the air, but their reign was no longer absolute. The world was still toxic, still breathless, but not hopeless. The first breath of Earth was heavy, dark and deadly. It hissed and fumed, a cocktail of gases that would make even the hardiest organism wince. And yet, that breath carried the seeds of everything to come. From volcano smoke and chemical haze came the foundation of oceans, the precursors of life, the story of air itself. So if you ever feel grateful for the clean, invisible oxygen you breathe now, take a moment to remember the time when the air would have melted your face. The Earth has come a long way from its first toxic exhalation. What began as a suffocating cloud of poison slowly transformed into the sky we now take for granted. It was in its own deadly way the planet's first inhale, its first whisper of existence. And maybe if you listen closely enough on a quiet night, you can still hear that echo deep in the wind. Don't breathe yet, but just wait. One day you will. The first oceans of Earth were not the tranquil blue mirrors we know today, nor the warm tropical havens that cradle coral reefs and whisper gently to the shore. No, the first oceans were born hissing and steaming, a bitter, churning brew that could strip metal and dissolve stone. They were the planet's first great experiment with water, but not yet with comfort. If you could have scooped a handful of that early ocean, it wouldn't have sparkled in sunlight, it would have frothed, fizzed, and stung. You might even imagine Earth herself, proud of her new creation, muttering playfully, "Go ahead, take a sip, but don't say I didn't warn you." It began as most things cosmic do, with collisions. The Earth, still young, still cooling, had been gathering moisture the way one gathers thoughts. Slowly, through persistence and chance, some of that water came from within, trapped in minerals that released steam as the planet's molten crust hardened. But much of it came from the heavens. Comets and icy asteroids, wayward travelers from the outer solar system, hurtled into Earth's surface, each one a delivery of frozen cargo. They arrived not gently, but explosively, their ice vaporizing on impact, feeding clouds of steam that wrapped the planet in shimmering veils. For countless years it rained, relentlessly, violently, the kind of rain that hammers rather than falls, rain that hissed against glowing rock and turned it instantly into plumes of steam. Drop by drop, deluge by deluge, the planet cooled, and the water began to settle. The steam condensed into sheets of liquid that filled the planet's low places, carving basins where continents would someday rest. In time, the water gathered, deepened, and finally, Earth exhaled its first great sigh, ocean. But these were no serene blue expanses. They were the color of iron and smoke, their waves thick with dissolved minerals, their surfaces reflecting a sky more copper than blue. Beneath them, the newborn crust still seethed with volcanic heat. Hydrothermal vents burst from the seafloor like open wounds, releasing plumes of carbon dioxide, sulfur, and metal-rich steam. If you dipped a thermometer into that early ocean, it would have read, not refreshing but scalding, perhaps 60, 70, even 100 degrees Celsius in places. It was a world that simmered rather than splashed. And those waters, those precious first waters, were acidic, not by accident, but by chemistry. Carbon dioxide, exhaled in endless clouds from volcanoes, dissolved easily into the oceans, forming carbonic acid, the same compound that gives soda its tang. The result, a global sea with a pH around 5 or 6, roughly the acidity of black coffee, perhaps a little worse. To modern life that would be unfriendly at best, corrosive at worst. It was as if the entire planet had been filled with a cosmic vinaigrette. You might imagine early Earth as a giant teapot filled not with tea but with carbonated acid water, bubbling merrily and saying, "Refreshing, not yet." But interest. The acidic oceans worked tirelessly, shaping the world in their own sharp way. They gnawed at the newborn rocks, dissolving minerals, releasing metals, and painting the seas with a strange chemistry of their own. Iron, nickel, magnesium, all leached from the crust, gave the oceans a dark, murky hue. More rust than blue, more smoke than light. The waves bit at the land like impatient sculptors, grinding down the edges of volcanic cliffs and carrying their dust into the deep. Every drop of water was a tiny blade, carving away at a world that didn't yet understand gentleness. Yet, in that chaos, there was beauty. The seas glowed faintly in the light of the young sun, reflecting colors that have long since vanished from the planet's palette. Imagine a world wrapped in orange skies, where the oceans shimmered with greenish light, where lightning danced across mist that smelled faintly of sulfur and stone. Steam drifted from the surface in long, ghostly ribbons, and beneath it all the planet cooled and hardened, its molten heartbeat slowing, its fever easing. The oceans, though harsh, were bringing balance. Chemically speaking, those acidic waters were busy. The dissolved carbon dioxide formed weak acids that reacted with silicate rocks, drawing out calcium and magnesium, creating the first carbonates and clays. These reactions were the beginning of what geologists now call the carbon cycle, a system that would, over billions of years, regulate the planet's temperature and make life possible. But at this stage, the balance was still crude. There was far too much CO2 in the air, far too little oxygen in the water, and the chemistry of the seas leaned sharply toward the sour. No living creature, not even the hardiest microbe, could have survived for long in that environment. The acidity alone would have shredded delicate membranes and destabilized the fragile molecules that life depends on. Amino acids, those tentative building blocks of biology, would have struggled to form in such conditions, their structures warped by the low pH. The ocean wasn't ready to nurture. It was still in its temperamental youth, still more cauldron than cradle. But oh, it was spectacular to watch. The interaction of acid and rock produced dazzling effects. Imagine cliffs fizzing where waves crashed against them, releasing clouds of carbon dioxide like slime. Rivers, heavy with dissolved minerals, poured into the sea, staining it in streaks of ochre and green. The air above the ocean shimmered with heat and mist, refracting sunlight into halo. Even sound would have been strange here, a constant low roar of steam, punctuated by the rumble of underwater eruptions. The world spoke in the language of chemistry, hissing, bubbling, reacting. Over time, as the planet continued to cool, the rains softened. The carbon dioxide levels in the air began to drop, as more of it was absorbed by the ocean and locked into minerals on the seafloor. The acidity lessened, slowly, stubbornly, but surely. The pH rose bit by bit, inching toward neutrality. Still, for millions of years, these early seas remained unfriendly, a reminder that water alone does not guarantee welcome. Earth had learned to hold its water, but not yet to make it kind. It's tempting to imagine these acidic oceans as cruel, but they were more like overzealous apprentices, too eager, too intense, learning their craft by trial and error. Every wave, every droplet, every chemical reaction was part of a long education. The water was learning how to balance itself, how to hold minerals without biting them, how to dissolve carbon without drowning in it. The planet, too, was adjusting, testing the boundaries of temperature and chemistry, experimenting with stability. And in that slow adjustment, the world was changing. The oceans, once as corrosive as vinegar, began to deposit minerals on the seafloor. Layers of carbonate and silicate formed, capturing carbon and easing the acidity. Volcanic eruptions, though still frequent, started to release less CO2 relative to what the oceans could absorb. The waters grew deeper, cooler, and more stable. Steam thinned into clouds, clouds condensed into rain, and the rain fell softer. Somewhere along the line, the pH crept up another notch. The seas, once sharp enough to sting, began to taste, well, not pleasant, but survivable. Still, those early days of acid water left their mark. The rocks that formed during that period carry the chemical scars, altered minerals, strange isotopic ratios, and the faint whisper of a planet still finding its footing. They are the diary pages of a world in transition, written not in words but in atoms. To geologists, those rocks are the planet's oldest memories, records of a time when water and stone were still arguing about who would shape whom. There's a certain poetry in that argument. Water, though gentle in our modern minds, was once Earth's most aggressive sculptor. It didn't erode, it attacked. It hissed into cracks, dissolved boundaries, and broke mountains down molecule by molecule. Yet, without that fiery partnership between acid and rock, the world might have remained barren. The acidic oceans carried nutrients from the crust into solution, iron, phosphorus, calcium, all of which would one day feed the chemistry of life. What began as corrosion became creation. It's humbling, isn't it, To think that the same oceans that now cradle dolphins and plankton once would have eaten them alive, that the gentle sound of waves today echoes the same forces that once boiled and burned. The sea has always been Earth's mirror, but in those first ages, it reflected a harsher truth. Beauty often begins as struggle. If you could stand by those first shores, though you'd need a very strong suit and an even stronger stomach, you might find it hauntingly beautiful. The horizon would glow orange beneath thick clouds. Steam would rise in sheets, curling upward to meet the dark sky. The water, black with minerals, would fizz softly at your feet, leaving white streaks of salts and metal deposits on the rocks. The smell would be sharp and metallic, like rust and vinegar and rain all at once. You'd watch bubbles rise, pop, and drift away as tiny ghosts of carbon dioxide whispering of reactions too complex to see. And somewhere beneath that surface, perhaps near a volcanic vent, perhaps in a quiet tide pool, the first chemical symphonies of life were quietly beginning to tune themselves. Not life yet, but possibility. The acidic oceans, despite their hostility, were laboratories of change. They dissolved, rearranged, and recombined the elements of the earth in countless ways. They built the molecules that would, one day, assemble into something that could swim, breathe, and dream. The ocean's hostility was also its genius. It refused to sit still, and in that restlessness lay the seeds of creation. Eventually, as the planet continued to cool and carbon dioxide levels dropped further, the oceans mellowed. Their pH rose to around 7. Then above, they turned from sour to neutral, from caustic to calm. The minerals they had carried for millions of years began to settle into sediments, forming the first stable seabeds, and the seas, now less corrosive, began to invite instead of repel. They became mirrors for sunlight, canvases for wind, cradles for chemistry, and eventually for life. The acidic oceans faded into memory, their legacy written in stone and element. But they were never failures. They were the necessary first draft of something grander, the world's first attempt at fluid grace. Their bite softened into balance, their sting into sustenance. Without them, the later life-giving seas could never have been. So the next time you gaze at the ocean, remember that it was once a vat of cosmic acid, foaming and spitting as it learned the art of being kind. The same water that now laps gently at the shore once dissolved mountains and boiled rock. It's the same water, only wiser, and perhaps, somewhere in its depths, the ocean still remembers its youth, when it was fierce, fiery, and just a little too sour for comfort. When the planet was young and the seas hissed with impatience, waiting for the day they could finally, gently cradle life. Between about 4.1 and 3.8 billion years ago, the Earth endured one of the most spectacular, catastrophic, and strangely productive tantrums in its history, a period known as the Late Heavy Bombardment. It sounds almost glamorous, like a cosmic air show, but in truth it was less fireworks and more apocalypse on repeat. Imagine a sky that never cleared, a surface that never cooled, and a planet that kept getting punched by rocks the size of mountains. If Earth had been a person, this was the phase where it would have said, "I can't catch a break, can I?" The Late Heavy Bombardment was exactly what it sounds like, an extended rain of asteroids and comets, pelting the young planets of the inner solar system. The Moon, Mars, Mercury, Venus, all took their share of hits. But Earth, sitting larger and closer to the gravitational influence of its neighbors, got the worst of it. To the best of our understanding, this cosmic barrage lasted a few 100 million years, long enough for every patch of newly solidified crust to be melted, vaporized, or shattered again. It was as though the universe, having spent eons building a planetary system, suddenly decided to throw a rock party with no curfew. No one knows for certain what caused this violent episode. The leading suspect is the gravitational mischief of the giant planets. Jupiter and Saturn, those vast bullies of the outer solar system, may have shifted slightly in their orbits, tugging on swarms of icy and rocky bodies left over from planetary formation. These displaced objects, millions upon millions of them, were flung inward like a rain of cosmic debris, colliding with anything unlucky enough to be in their path. Earth, freshly cooling, still young and volatile, became a magnet for mayhem. To picture what this meant, imagine an asteroid the size of Manhattan hitting at 20 kilometers per second. That's not just a splash, it's a detonation with the energy of millions of nuclear bombs. The impact would have blasted a crater carbon of kilometers wide, melted the surrounding crust, and sent vaporized rock shooting into space. For a few minutes, the ground itself would have behaved like liquid. Entire regions would have glowed red hot, rivers of molten rock spreading across the landscape. And that was just one impact. During the late heavy bombardment, such events happened again and again, sometimes daily, sometimes hourly, like the universe had set an alarm for destruction and forgot to turn it off. From the surface, if you could somehow survive to watch, it would have been a nightmare made of light. The sky was never dark. Fireballs streaked across it constantly, some glowing faintly, others flaring so bright they lit the landscape brighter than the sun. The air trembled with shock waves. Every impact launched plumes of molten rock and debris high into the sky, where it rained down again as fiery meteors, turning night into a curtain of sparks. Entire oceans, if they had formed, boiled away in great clouds of steam. The planet was in a constant fever, the surface remade again and again until no original feature remained. Geologists estimate that during this period, as much as 10% of Earth's surface could have been melted at any given time. Vast seas of lava pooled in the basins left by giant impacts. Volcanoes were triggered everywhere, their eruptions merging with the chaos from above. The atmosphere thickened with vaporized rock and gas, trapping even more heat and making the planet glow faintly red from space. To call it uninhabitable would be an understatement. It was an oven wrapped in thunderstorms. Even the crust itself struggled to survive. Each impact cracked it open anew, mixing molten and solid rock in a geologic soup. And yet, for all its violence, this bombardment was not pure destruction. It was also delivery. Every comet that slammed into Earth brought a little bit of something precious: water, carbon compounds, nitrogen, and other ingredients that would eventually make life possible. So while each impact burned, boiled, and melted, it also stocked the pantry. You could think of it as the universe's version of a tough love recipe. First, set the oven to apocalypse, then add water and stir. Of course, at the time, any attempt at forming life would have been doomed. Molecules might have begun to assemble in pools between impacts, only to be vaporized the next day. If any primitive chemistry dared to whisper, "Hello, another asteroid," would promptly answer with boom, the planet was trying to create. But the cosmos kept pressing the reset button. Scientists sometimes call this impact frustration, and it's an apt phrase. The world was eager to get started, but the sky refused to stop throwing things. The evidence for this chaos survives not in Earth's own crust, most of which has long since been recycled by plate tectonics, but on the moon. Its surface, unchanging and unprotected, still bears the scars of that time. Immense basins like Imbrium, Nectaris, and Serenitatis, each a fossilized memory of impacts so huge that debris from them must have reached Earth. The lunar record is like an old battlefield map, showing us how heavily the bullets of the cosmos once fell. And because the moon has no weather, no tectonics, no oceans to erase its history, it still holds the pockmarked truth. The inner solar system 4 billion years ago was not a calm neighborhood. Back on Earth, the bombardment didn't just scar the surface, it reshaped the planet's very personality. The constant impacts churned the crust and mantle, mixing materials from deep within with those from space. Some of those collisions may have triggered the early segregation of elements, helping iron sink toward the core and lighter silicates rise toward the surface. Others created transient atmospheres of vaporized rock, only for them to condense again into minerals and rains of molten glass. It was an endless cycle of destruction and renewal, as if the planet couldn't decide whether it wanted to be solid, liquid, or gas. Let's pause to appreciate how absurdly energetic this period was. A single large asteroid impact could raise global temperatures by hundreds of degrees for years, vaporize entire oceans, and launch enough debris into orbit to briefly give Earth a halo of glowing rock dust. Multiply that by thousands, and you begin to grasp the scale. The Earth of 4 billion years ago wasn't a single surface. It was thousands of surfaces, replaced again and again, layer upon layer of catastrophe. If you could fast forward through time, you'd see continents forming and disappearing, seas boiling away and refilling, mountains rising and falling, all in dizzying succession. It was geology set to fast forward. And yet, even chaos has its rhythm. Over time, the intensity of the bombardment began to fade. The supply of leftover asteroids dwindled as they were either absorbed into planets, slung out of the solar system, or simply broke apart. Impacts became less frequent, though still deadly when they occurred. The Earth's crust, though scarred and thin, began to hold together for longer intervals. The seas that had evaporated hundreds of times began to persist. The air, heavy with dust and gas, began to clear between impacts. Slowly, hesitantly, the planet was calming down. Still, the scars of that age never truly vanished. Every mountain and ocean basin that formed later was built atop the wreckage of those early impacts. The chemical fingerprints of meteorites remain in ancient rocks, extraordinary isotopes of tungsten and platinum that hint at how much extraterrestrial material rained down upon us. Even today, a tiny percentage of the metals in your body, iron, nickel, platinum, owe their origin to that rain of stone and ice. You, in a very literal sense, carry the dust of that storm within you. It's difficult to overstate how hostile Earth was during those years. Every time it seemed to cool enough for stability, another impact would undo the progress. The oceans would vaporize into steam, the sky would fill with molten droplets, and the surface would glow like an ember. Imagine standing on a shore, if one existed long enough to stand on, and watching the horizon erupt as a comet slammed into the sea. The shockwave would flatten everything for hundreds of kilometers, and a tsunami taller than any skyscraper would race outward, followed by a rain of molten glass. The air would heat to several hundred degrees. Survival would be impossible, but the view, if you could somehow observe it safely, would be breathtaking, terrifying, yes, but grand beyond comprehension. The bombardment also influenced the chemistry of the oceans and atmosphere that followed. Every impact released gases from both the incoming body and the rocks it struck. Carbon dioxide, sulfur, water vapor, and metals. These additions thickened the air, changed its color, and seeded the skies with new compounds. Some impacts may even have temporarily generated small magnetic fields or shock-driven lightning storms, further fueling the planet's restless chemistry. If life was destined to arise here, these violent gifts from space provided both the raw ingredients and the persistent reminder that existence would never be simple. As the final centuries of the bombardment passed, the intervals between impacts stretched. Earth's surface, though still hot and unstable, began to retain features long enough for water to gather again. The oceans refilled, their surfaces steaming but persistent this time. The atmosphere, though still heavy, began to stabilize. The sky, once an unbroken inferno, might occasionally show the faintest hint of blue, and somewhere, in a quiet pocket of that still hostile world, the first fragile chemical whispers of life began to stir again, small, uncertain, but patient. It's oddly poetic that life's cradle would be sculpted by such destruction. The same asteroids that annihilated the planet's surface also delivered the water and carbon compounds essential for biology. The same impacts that boiled the oceans also stirred their chemistry. The violence of the bombardment didn't just threaten life, it prepared the ground for it. It was as though the Earth needed to be shaken, mixed, and reforged before it could become the gentle blue world we know. By about 3.8 billion years ago, the Great Storm was finally winding down. The last major impacts dwindled to sporadic visits, still dramatic, but no longer planet-shattering. The crust grew thicker and cooler. Oceans stopped evaporating completely between strikes. The night sky quieted. The moon's surface, once glowing from molten scars, hardened into the cratered face we still see. And for the first time in hundreds of millions of years, Earth had something it had never known before: stability. If you were to step into that final twilight of the bombardment, you might see a world still scarred and smoking, but no longer aflame. The ground would be black and glassy from repeated meltings. Craters would stretch for hundreds of miles, filled with simmering pools of mineral-rich water. Steam would rise in gentle plumes, not violent geysers. The stars, faint but visible through the thinning atmosphere, would reflect on the cooling seas. It was, at last, a world with potential. The late heavy bombardment was a long and chaotic chapter, written in fire and stone. It erased landscapes, vaporized oceans, and delayed life's beginning by hundreds of millions of years. But it also set the stage, It delivered the ingredients, stirred the pot, and forged the world's character. The Earth that emerged afterward was tougher, richer, and more balanced, a survivor ready for the quieter miracles to come. So when you look up at the moon tonight and trace the dark patches of its craters, remember that each one is an echo of that storm, a fossilized memory of the time when our world was under siege. Those same impacts that scarred the moon once shaped the Earth. The rain of fire is long gone, but its legacy remains in every breath, every drop of water, every atom of metal we hold. In the end, the bombardment was not just chaos, it was creation in disguise. Earth was forged in collisions, tempered in fire, and polished by catastrophe. And after the last stone fell from the sky, the planet stood silent beneath a clearing heaven, steaming, scarred, but finally still, ready, at last to dream. Around 2.4 billion years ago, the Earth did something extraordinary. It learned how to breathe, not in the way lungs expand with air, but in the deeper, chemical sense. After nearly 2 billion years of suffocating under a toxic sky, the planet began to change from within. Quietly and irrevocably, the world that had once choked on methane and carbon dioxide suddenly found itself exhaling oxygen, and nothing would ever be the same again. This turning point is known as the Great Oxidation Event, Earth's first great act of domestication, the moment it began to tame itself. To imagine the world before that event is to imagine a planet ruled by poison and shadows. The oceans were greenish and murky, heavy with dissolved iron and sulfur. The air was thick and foul, dominated by gases that would make modern creatures faint. Methane kept the world warm, carbon dioxide kept it acidic, and oxygen precious. Invisible oxygen was almost non-existent. The planet was thriving, in a way, but it was a kind of thriving that didn't care about us. The only living things were microbes, invisible to the eye but mighty in their persistence. They lived in deep seas and shallow pools, feeding on minerals and chemical gradients, turning rocks into energy and energy into survival. They were hardy, they were resourceful, and they were about to change everything. Somewhere in that alien ocean, a group of microscopic pioneers made a revolutionary discovery: sunlight. These tiny beings, ancestors of what we now call cyanobacteria, learned how to use light as fuel. Instead of breaking down chemicals for energy, they captured the glow of the sun and turned it into life. In doing so, they stumbled upon one of the most transformative reactions in the history of the universe: photosynthesis. It was elegant and efficient. Take in sunlight, water, and carbon dioxide, and out comes energy. And as a byproduct, that oxygen at first had nowhere to go. The early atmosphere and oceans were filled with iron and other reactive minerals, just waiting for something to combine with. The oxygen released by these new photosynthetic microbes didn't accumulate in the air. Instead, it was immediately consumed by chemistry, oxidizing iron, sulfur, and methane in a frenzy of reactions that changed the very color of the world. If you could have seen it happen, you might have watched as the greenish oceans slowly turned red, stained with rust. It was as though the entire planet was corroding at once, and in a sense, it was. This global rusting left behind one of Earth's most remarkable geological records, the banded iron formations. These are layers upon layers of rock, alternating stripes of dark iron oxide and lighter silica that can still be seen today in ancient deposits from Australia to Canada. They are the fossilized echoes of that first great oxidation, the signature of a world literally reacting to its own transformation. Each layer tells the same story. Oxygen was released, iron oxidized, then the process paused and started again. It was a rhythmic dance between biology and chemistry, a planetary-scale symphony of rust. The oceans, once teeming with dissolved iron, became clearer as that iron fell out of solution, settled onto the seafloor. The sky above, still hazy with methane, began to thin. The balance of gases shifted. At first it was subtle, too subtle for any microbe to notice. But over millions of years, oxygen levels began to creep upward. For the first time, Earth had something new in its atmosphere, a molecule that could burn, energize, and eventually sustain. To the cyanobacteria, this was just business as usual. They weren't trying to terraform the planet. They were just living their microscopic lives, exhaling oxygen, the way we exhale carbon dioxide, but their breath was planetary alchemy. The gas they released didn't just linger, it reacted, reshaped, and redefined. Methane, once abundant, began to oxidize into carbon dioxide and water vapor, reducing the greenhouse effect and cooling the planet dramatically. The Earth entered one of its first great ice ages, a sudden chill after a long, steamy adolescence. It's one of history's great ironies. The tiny architects of breathable air accidentally triggered a global freeze. If the planet had a voice then, you might imagine it groaning, a bit too much freshness perhaps. The cyanobacteria, unbothered, kept on photosynthesizing. They covered shallow seas in vast colonies called stromatolites, layered mounds of microbial mats that still exist in a few places today. Each one was a tiny oxygen factory, bubbling steadily into the water and sky. Slowly the world began to change color again. The rusty oceans turned clearer, the skies paled, and sunlight began to pierce the atmosphere more deeply. For the first time, Earth's chemistry was beginning to stabilize into something recognizable, something that could one day support forests, fish, and breathing animals. But for many of the planet's older inhabitants, this was not a miracle. It was a disaster. Oxygen, that miracle molecule for us, was a deadly toxin for most of the anaerobic microbes that ruled the early world. To them, it was like acid, burning through cell walls, destroying delicate chemical pathways. As oxygen levels rose, vast swaths of microbial life were wiped out. It was the first mass extinction in Earth's history, an invisible apocalypse that left the survivors to adapt or vanish. You could call it the Great Oxidation Revolution, but it was also the Great Purge. The Earth was cleansing itself chemically, and in doing so it killed off much of what had come before. It was as if the planet had decided to hit the reset button, trading a world that ran on chemical smoke for one that would someday sparkle with blue skies and green plants. And perhaps if you squint at it from the right angle, you might see a touch of dark humor in the story. The very thing that would make life possible was, at first, the ultimate poison. Oxygen, life-giver, destroyer, and the planet's most paradoxical invention. The Great Oxidation Event didn't happen overnight. It took hundreds of millions of years for oxygen to accumulate in meaningful quantities. The atmosphere shifted from trace amounts, mere whispers of O2, to concentrations that could sustain more complex metabolisms. Over time, the iron in the oceans ran out of appetite for oxidation, and the excess oxygen began to linger. The planet's chemistry flipped. The air that had once been a soup of carbon dioxide and methane became something new, lighter, and cleaner. If you could have visited Earth then, you'd have seen skies turning from orange to blue for the first time. It was the dawn of clarity. Geologically, this transformation is one of the most profound events in Earth's history. It altered the color of rocks, the texture of sediments, the acidity of oceans, and the course of evolution itself. Oxygen opened up entirely new chemical pathways for life. It allowed for energy-rich metabolisms, for cells to grow larger and more complex. In short, it laid the foundation for everything multicellular that would follow. It was quite literally the breath before life as we know it. Still, the planet didn't turn into paradise overnight. For long stretches, oxygen levels fluctuated wildly, spiking and dropping as the balance between photosynthesis and volcanic outgassing wavered. There were times when the world nearly lost its newfound breath, when volcanoes spewed out enough, reducing gases to consume the oxygen again. But each time, the microbes persevered. They had found their rhythm, and the planet was slowly learning to keep pace. The legacy of that transformation is visible everywhere today. Every flake of rust on a forgotten tool, every streak of red in ancient rocks, every breath we take, they all trace back to that first great oxidation. When you breathe, you're participating in a conversation that began 2.4 billion years ago between light, water, and tiny blue-green cells. Those cells didn't know it, but they were teaching the planet how to sustain a heartbeat. And Earth, for its part, was listening. The iron in the crust oxidized, forming massive deposits of hematite and magnetite, resources that would one day feed human industry. The skies cleared, allowing sunlight to reach the surface without the orange filter of methane haze. Ultraviolet radiation, once deadly, began to be filtered by the thin but growing layer of ozone formed from oxygen high in the atmosphere. The world, once hostile and opaque, was turning transparent. The Great Oxidation Event marked the beginning of Earth's long road to habitability. It was the first step in a slow taming, a cosmic house training of a wild, reactive planet. You could say this was when Earth stopped being a raw experiment in chemistry and started behaving like a home. It took patience, persistence, and of course microbes with a flair for innovation. But eventually the air itself became a living thing, pulsing with oxygen, connecting ocean to sky, microbe to mountain. It's a funny thought. The planet's first great environmental movement wasn't led by intelligent creatures with tools, but by bacteria no bigger than dust motes. They had no agenda, no awareness, no plan, and yet, through sheer metabolism, they redefined the meaning of living world. They gave us the air we breathe, the iron in our blood, the rust on our ships, and the sunsets that glow orange before fading into blue. All of it traces back to those little architects of oxygen, tirelessly photosynthesizing in shallow seas long before the first leaf unfurled. So, if Earth could speak now, perhaps it would look back on that era with a mix of pride and amusement. Yes, it might say, I was a bit of a mess before the oxygen. The air was thick, the water was sour, and the place was always on fire. But once those little microbes started bubbling oxygen, I finally began to calm down. I began to breathe. The Great Oxidation Event wasn't just the rise of oxygen. It was the moment the Earth learned balance, the beginning of everything that breathes, burns, and builds. From that point on, the atmosphere was no longer a passive veil, but an active participant in life. The planet had entered a new conversation with itself, sky with ocean, air with stone, life with chemistry. It was the start of a long, evolving dialogue, one that continues every time a leaf unfolds, a wave foams, or a creature like you takes a deep, grateful breath. And if you exhale softly now, you might smile at the thought that your breath, the one leaving your body this very second, is part of that same ancient rhythm. It's the echo of microbes that turned poison into promise, darkness into light, and chaos into air. The Great Oxidation was not just a planetary event. It was Earth's first act of self-care, its way of saying, let's make this place livable. It rusted the rocks, froze the world, and rewrote the atmosphere. But in the end, it gave us something better than gold. It gave us breath. There was a time when Earth's oceans were moody, temperamental things, hot, acidic, and quick to bite. They fizzed with carbon dioxide and hissed against rock, a planetary soup with the personality of vinegar. But slowly, over millions upon millions of years, they began to calm. Their anger softened, their chemistry changed, and their taste, if one could somehow dip a finger, went from liquid rock to something approaching drinkable. This was the long, patient process of oceanic taming, when the seas that once corroded stone learned to cradle life instead. If the Earth could have spoken then, it might have said, there, I've cooled down. You can swim now. Probably. It began deep beneath the waves, with the quiet conversation between water and stone. The planet's crust, mostly basalt dark, volcanic, and rich in minerals, was busy performing one of the greatest chemical balancing acts in Earth's history. Basalt, as it turns out, has a remarkable appetite for carbon dioxide. When rain fell and rivers carried dissolved CO2 into the ocean, the gas reacted with the minerals in basaltic rock, things like calcium, magnesium, and iron silicate. These reactions pulled carbon out of the water and locked it into solid carbonates, minerals that sank to the seafloor and rested there, safe and stable. Every reaction was a tiny act of peacekeeping, a microscopic mediation between fire and acid. With each new deposit of carbonate, the ocean lost a little of its sourness. The pH, once low and corrosive, maybe around 5 or 6, began to climb toward neutrality. It was an invisible, patient transformation, like watching anger cool into patience. Drop by drop, reaction by reaction, the planet was learning restraint. Meanwhile, the volcanic exhalations that once filled the air with carbon dioxide began to slow. The world was no longer a furnace. Its heartbeat had steadied. The thick blanket of greenhouse gases thinned slightly, letting the Earth's surface cool just enough for the chemistry of stability to take root. And the oceans, always reflective of the sky above, mirrored this newfound calm. Their surfaces ceased to steam. Their colors began to shift from murky green-brown to something clearer, more open to light. The basaltic crust beneath the waves did more than neutralize acid. It began to shape the future of continents. As water seeped into cracks and reacted with hot rock, it altered the crust's chemistry, producing lighter minerals that could float atop the mantle. This was the geologic seed of continental crust, the first outlines of stable landmasses that would rise and stay risen. The continents in their earliest forms were the children of oceanic taming, born from the gentle but persistent dialogue between acidic water and volcanic stone. You could almost think of the Earth at this point as an alchemist, experimenting with balance, adjusting ratios, blending fire and water until it found the right recipe. Too much CO2 and the oceans would boil with acid again. Too little and the planet might freeze. The chemistry of the seas became the planet's thermostat, with basaltic rocks as the dials. Whenever volcanic gases raised the acidity, the rocks quietly absorbed the excess, locking it away in mineral form. It was a feedback loop, a natural self-correction system that would keep the oceans roughly neutral for billions of years to come. From a distance, this would have been an age of tranquil transformation, though it was anything but silent. The seafloor sizzled with hydrothermal vents, those underwater chimneys that belched mineral-rich plumes into the depths. Their hot fluids carried metals and gases into the ocean, adding complexity to the chemical mix. Around these vents, strange chemistry was at play. Chemical gradients, energy flows, reactions that made the first whispers of organic molecules possible. The water's new balance, neither too acidic nor too alkaline, provided a stable playground for molecules to survive long enough to react, combine, and eventually evolve. The ocean's newfound neutrality was more than a chemical milestone, it was an invitation. Life, primitive, microscopic, and fearless, could now begin to take root. The balance of acidity meant that delicate organic structures like lipids and amino acids could persist without falling apart. Iron and other metals, no longer bound entirely by acid, could act as catalysts for early metabolic reactions. In short, the chemistry of life had found its stage. The shift in ocean chemistry also had a profound effect on the appearance of the planet. The seas, once stained by dissolved metals, began to clear as those metals precipitated out into sediments. The waters reflected more light, shimmering blue-green under the sun. The world's first continents, their surfaces cooled and solidified, peaked above the waves like newborn islands. Rivers carrying sediment and carbonates meandered across these young lands, delivering nutrients back to the sea. It was a planetary circulation system, a conversation between land and ocean that would never stop. Even the air above began to reflect this growing balance. As more carbon was locked into rocks and less lingered in the atmosphere, the greenhouse effect moderated. Temperatures dropped just enough for the water cycle to stabilize. Rain fell, rivers flowed, evaporation rose. It was a delicate dance choreographed by chemistry. The Earth for the first time was no longer at war with itself. But let's not pretend the oceans became friendly overnight. They still had moods. Local volcanoes could spike acidity in an instant. Hydrothermal vents could create pockets of extreme chemistry where life, if it existed, had to adapt fast or perish. Yet overall, the trend was clear. The oceans were maturing. They were moving from chaos to equilibrium, from corrosive to kind. If the early seas were a cauldron, the new ones were a simmering pot, still hot, still bubbling, but controllable. This long chemical negotiation had an artistic side too. As the basalt reacted with carbon dioxide, the oceans began to sparkle with the first mineral precipitates, tiny crystals of calcite, dolomite, and siderite, drifting like stardust through the water. When they settled, they formed layers of carbonate rock that would one day tell geologists the story of this transformation. Each layer was a page in the planet's diary, written in minerals instead of words. Today, I grew calmer. Today, I learned balance. And as the oceans lost their bitterness, they gained complexity. The neutral pH allowed new kinds of chemical reactions, longer carbon chains, more stable organic molecules, more intricate networks of energy exchange. Somewhere in that vast warm water, perhaps near a volcanic vent or in a quiet tidal pool, the first protocells assembled. They weren't alive in any modern sense. but they were close membranes enclosing reactions, little chemical islands learning to copy themselves. The ocean's neutrality wasn't just comfort, it was permission. Meanwhile, the continents grew in confidence. The basaltic crust that had once dominated began to give way to lighter granite, born from partial melting deep beneath the early landmasses. This granite was more buoyant, more stable, and it resisted erosion better than its darker cousins. With continental crust came permanence, land that could last for eons, withstand the tides, and provide a stable platform for ecosystems yet to come. You might say the Earth was finally learning to hold its shape. The dance between rock and water continued. As fresh basalt formed at mid-ocean ridges, it reacted with seawater, pulling carbon out of the ocean and replacing it with minerals. As continents eroded, they fed calcium and magnesium back into the seas, maintaining the balance. The pH of the oceans hovered between 7 and 8, nearly neutral, but just alkaline enough to support carbonate chemistry, the foundation of shells, corals, and bones that would appear billions of years later. The stage was set for complexity. If you could have stood by one of those early shorelines, you might not have recognized it as Earth. The waves would have lapped against dark rocks streaked with pale mineral crusts. The air would have smelled faintly metallic, like rain on hot stone. The water, though no longer sour, would still be rich with dissolved minerals, tasting faintly of salt and stone dust. And beneath its surface, in the dim light, filaments of early microbial mats might already be forming, tiny shimmering blankets of life clinging to rocks, exhaling gases and marking the slow dawn of biology. The neutralization of the oceans didn't just make life possible, it created feedback loops that would sustain it. As organisms began to emerge and photosynthesize, they influenced the chemistry of the seas, even further, drawing down carbon dioxide, releasing oxygen, and forming new mineral deposits. The interplay between biology and geology became inseparable. Life shaped the oceans, and the oceans shaped life. It's almost funny to think that all of this started with a simple chemical reaction, carbon dioxide meeting basalt. That humble process, no more glamorous than stone fizzing in acid, set off a cascade that would lead to continents, climate regulation, and eventually consciousness. The planet's temper cooled not because of magic, but because of patience. Basalt, the quiet worker, absorbed the fury of the early world and turned it into stability. By the time the oceans reached a steady pH, they had become the true heart of the planet, a vast circulatory system of balance and renewal. They were no longer the enemy of rock, but its partner. Water dissolved stone, stone softened water. Together they wrote the long story of equilibrium that still continues today. And maybe, if you listen to the sea on a calm day, you can still hear the echo of that transformation. The gentle hiss of waves against rock, the slow whisper of chemistry at work. It's the sound of a planet remembering how to breathe evenly. So the next time you stand by the ocean, take a moment to appreciate its long journey from acid to calm. That gentle water, licking your feet, was once a seething potion that could eat through mountains. It's been tempered by eons of reaction, patience, and stone. What began as a corrosive cauldron became the cradle of life. In the end, Earth's great taming wasn't done by force, but by chemistry, the quiet persuasion of basalt and water, the slow erosion of chaos into harmony. The oceans, once sharp enough to sting, became mild enough to nurture. The continents rose from their depths, steady and strong, and somewhere in those softening seas, life began to stir and smile, as if whispering back to the earth, "Thank you, I can breathe now." After hundreds of millions of years of cosmic chaos, something miraculous happened. The bombs stopped falling. The universe, it seemed, had finally run out of rocks, or at least run out of the patience to throw them at Earth. The endless storm of asteroids, comets, and cosmic shrapnel that had battered the planet since its fiery youth began to ease. The skies grew calmer, the ground stopped trembling every few weeks, and for the first time in its long molten memory, the Earth could take a breath without being punched by the heavens. You could almost imagine the planet sighing in relief and muttering, "Finally, a little peace and quiet." This great lull, the era after the late heavy bombardment, marked a turning point in the planet's story. Between about 3.8 and 3.5 billion years ago, the constant barrage of meteorites that had once boiled oceans and shattered crust began to fade into the background. Impacts didn't vanish completely. After all, the solar system was still young and messy, but they became rare enough that Earth could finally begin to hold on to what it built. The surface stopped being reset every few thousand years. The air stopped being blasted away. The seas, the crust, and the sky could finally start a long, uninterrupted conversation. To understand what a relief this was, picture the Earth before this calm, a planet with post-traumatic stress. Every time a comet struck, it erased millions of years of geological progress. Oceans vaporized, only to rain down again. The crust cracked and melted. Whatever fragile chemistry might have begun in a quiet pond or volcanic vent was obliterated in an instant. It was like trying to write a novel while someone kept setting your notebook on fire. The Earth wanted stability. It needed a break from catastrophe. And now, at last, it was getting one. Scientists believe the slowdown in impacts was not random. The solar system had simply matured. The great gravitational shuffle that sent waves of asteroids inward had finished its dance. The leftover debris from planet formation, those endless fragments of rock and ice, had mostly been swept up, either colliding with planets, merging into moons, or being flung into distant orbits by Jupiter's immense gravity. What remained was smaller, scattered remnants, occasional wanderers rather than an army of destruction. Space itself had grown tidier, calmer, almost civilized. From Earth's perspective, this was revolutionary. Without constant bombardment, the planet's crust could finally solidify into something resembling permanence. The endless cycle of melting and refreezing slowed. The atmosphere, no longer blasted away by colossal impacts, began to thicken and stabilize. Steam condensed into clouds. Rain fell, and this time it stayed. Oceans could form and persist without being boiled off. The planet was cooling, settling, exhaling. The silence after chaos was deafening. Of course, silence is relative. Volcanoes still rumbled, earthquakes still cracked the crust, and smaller meteors still occasionally announced their presence with spectacular light shows. But compared to what had come before, this was serenity. For the first time, weather patterns could develop without being interrupted by cosmic explosions. The air could hold its chemistry for more than a heartbeat. Sunlight could shine for months or even years without being blocked by the soot of an impact. The Earth, after billions of years of bombardment, was finally getting a chance to grow up. Imagine standing on this newly peaceful Earth. The skies are no longer filled with fire. The stars are visible now, though the sun is still hazy behind thin volcanic clouds. The ground, though scarred, is solid. The air smells faintly of minerals and water vapor instead of sulfur and smoke. You might hear the gentle hiss of steam rising from cooling lava fields, or the soft rush of wind over bare rock. The horizon stretches unbroken. No mushroom clouds, no molten seas. It's still a harsh world, yes, but it's a world with potential. In this newfound calm, time began to stretch. The pauses between catastrophes lengthened from thousands of years to millions. In those vast intervals, the planet's surface chemistry could finally settle into patterns. Elements could cycle, water could flow, sediments could accumulate. For the first time, the Earth was no longer being built. It was beginning to live. The calm also changed the atmosphere. The constant impacts of the bombardment had once blasted vast quantities of gas into space, preventing any stable air from forming. Now, with fewer interruptions, volcanic gases, carbon dioxide, nitrogen and water vapor could linger long enough to build a proper atmosphere. It wasn't breathable yet, but it was loyal. It stayed. And that consistency meant that heat could be trapped, pressure could build, and the planet could maintain a more stable climate. It was, in a sense, the first version of Earth's weather. This stability had another quiet effect. It allowed the surface to cool enough for geological recycling to begin. With a solid crust and internal heat still bubbling below, plate tectonics began to stir, slowly, cautiously, like a giant stretching after a long sleep. The crust cracked, drifted, and recycled itself, bringing fresh material up from below and burying old rock into the mantle. This motion would become the planet's heartbeat, a rhythm that continues even now. But in those early days, it was a brand new trick, one made possible only because the impacts had finally given it a chance. It's tempting to romanticize this period as Earth's peaceful dawn, But in truth, it was more of an uneasy truce. The universe hadn't forgotten about us. It had just grown bored. Smaller asteroids still found their way to Earth now and then, leaving craters that dotted the young continents like freckles. But these impacts were pinpricks compared to the world-ending collisions of the past. If the late heavy bombardment had been a drum solo of destruction, this was the soft percussion of occasional meteors, a rhythm that the planet could live with. And with that calm came creativity. The oceans, stable and persistent now, could begin to act as giant laboratories of chemistry. Sunlight filtered through clouds, striking the water and driving reactions between minerals and molecules. The atmosphere, less violent, allowed UV light to play its part without incinerating everything. The Earth had moved from constant reset to gradual progress. The stage was finally steady enough for life's first experiments to begin. One can almost imagine the Earth, after so much chaos, feeling a bit dazed by the quiet. The absence of fire and fury must have been strange, a kind of cosmic hangover, but the silence was productive. With every century of calm, new minerals formed, new structures appeared, new balances emerged. The scars of ancient impacts weathered into softer shapes. The great craters filled with water and sediment, turning from wounds into basins. The air thickened, and the faintest hints of color blew from scattering sunlight, white from clouds, began to replace the rusty hues of the old methane-rich skies. Somewhere out there, the moon, born from the same chaos, was watching. Its own cratered face was a record of everything Earth had endured. Unlike its younger sibling, it would never heal, never change. But Earth, dynamic and alive, was already beginning to erase its scars. Wind and water, those gentle sculptors, were smoothing what once had been jagged. The planet's violence was giving way to rhythm. In a sense, this was the moment Earth graduated from cosmic infancy. The tantrums were over. The toys, asteroids, and comets had been put away. The planet was no longer being shaped by brute force, but by subtler, internal processes: erosion, tectonics, chemistry, and time. The solar system, too, had settled into a calmer order. The planets followed stable orbits. The asteroid belt had been tamed by Jupiter's gravity. The chaos of creation was giving way to the serenity of structure. It's easy to overlook just how precious that calm was. Without it, life could never have taken hold. Stability is the unsung hero of existence. For billions of years, the Earth had all the ingredients for life: water, carbon, energy, but no time between disasters to let them mix properly. Now at last, the recipe could simmer without interruption. The cosmic kitchen had stopped shaking long enough for the dough to rise. This period of peace also allowed Earth's internal systems to synchronize. The heat flow from the core established convection currents in the mantle, driving plate motion. Volcanoes released gases at a pace the atmosphere could handle. Weather cycles found their balance. The planet was learning, quite literally, to regulate itself. If the early Earth had been a wild teenager, this was a delta, still unpredictable at times, but much more composed. And yet, traces of the old chaos still lingered. Occasionally, a meteor the size of a mountain would crash through the atmosphere, reminding the planet of its turbulent past. But instead of total annihilation, these impacts now became mere punctuation marks in the story. The Earth could shrug them off, heal, and continue. Even destruction had lost its edge. Over time, the frequency of impacts continued to decline. The solar system became quieter still, its debris either consumed or exiled. The great vacuum of space began to feel, if not friendly, then at least indifferent. The Earth had earned its peace. It had survived fire, fury, and endless bombardment, and now it stood scarred but resilient, a world of calm seas and cooling skies. If you were a wandering traveler from another galaxy passing by the solar system at that moment, you might have noticed the Earth beginning to glow differently. Its surface reflected light from real oceans now, not molten rock. Its atmosphere shimmered faintly, no longer opaque with soot. It was a planet at peace, learning to breathe rhythmically, slowly preparing for the astonishing complexity that lay ahead. The Earth's new calm was not just a geological lull, it was a moral shift in the planet's personality. It had learned moderation, it had learned patience. The age of constant catastrophe had given way to an age of potential. The quiet was not empty, It was fertile. Every ripple in the sea, every flicker of lightning in the sky, every molecule that lingered long enough to combine with another was a sign of what was coming. And perhaps if you listen closely to the hum of the world today, the sigh of wind, the crash of distant waves, you can still hear that ancient transition, the moment when Earth moved from survival to possibility. It's the echo of a time when the cosmos, after billions of years of chaos, simply ran out of energy to destroy, and in that pause, creation began. The meteor storms had ended, the bombardment was over, and the universe, at least for a while, took a breath. The Earth, battered but unbroken, lifted its face toward the calm skies and said, "Finally, it's safe to stay." At long last, the Earth began to find its footing. After billions of years of fire, bombardment, and boiling seas, the restless planet started to grow something it had never known before. Land that lasted, not fleeting islands of volcanic froth, not molten crust that sank back into the depths, but real, enduring continents. The age of drifting magma and shattered surfaces was ending. The age of continents, the solid bones of the world, had. You could think of it as the Earth standing up for the first time, stretching its molten spine and planting its feet. The surface, once a restless sea of lava and storm, began to rise and hold. Plate tectonics, the slow, grinding ballet of Earth's crust, found its rhythm. A mantle churned below, convection currents rolling like slow thunder, pushing and pulling on great slabs of rock above. Where those slabs met, they collided, cracked, or dove beneath one another, giving birth to volcanoes and mountain ranges. It was noisy, messy, and profoundly creative, like watching a sculptor who worked in earthquakes instead of clay. At first, the continents were small and scattered, tiny rafts of buoyant rock, lighter than the dense basalt of the ocean floor. They floated on the molten mantle like crumbs on a simmering soup, drifting, merging, and breaking apart. Each new collision built more land. Each eruption added new layers. Volcanoes, those tireless architects of the early world, spat out lava and ash that cooled into solid ground. Layer by layer, eruption by eruption, the continents grew, patchwork quilts stitched together by fire. The key ingredient in this slow continental recipe was silica. Unlike the dark, heavy basalt that formed the ocean crust, silica-rich magma was lighter and more viscous. When it cooled, it created granite, tough, buoyant, and stable. Over time, these granitic materials began to dominate the rising land masses, forming the roots of the first true continents. They were the planet's anchor points, resistant to melting, resilient to time. The Earth had finally learned how to build something that wouldn't. But even the strongest rock needed shaping, and for that, the planet turned to its newest tools: wind, rain, and rivers. The atmosphere, no longer suffocating with carbon dioxide and methane, carried moisture across the globe. Clouds gathered, storms rumbled, and rain fell in earnest. Droplets that once sizzled on hot rock now soaked into the soil. Water began its ancient work of erosion, carving valleys, wearing down mountains, and carrying sediments toward the sea. In the grand laboratory of geology, erosion is both a destroyer and a creator. Every mountain it wears away becomes the silt and sand that feed the plains. The continents were learning how to breathe. Every river that cut through rock carried minerals toward the coasts, enriching the waters and building fertile deltas. Every storm that battered a mountain carried away the dust of creation. Over time, this process created the first soils, primitive mineral-rich layers that blanketed the land in fine powders of iron, silica, and clay. They weren't yet the lush, life-filled soils of later ages, but they were the foundation, the first beds upon which life could one day cling. From space, the Earth would have looked transformed, no longer a planet of endless ocean and volcanic glow. It now bore patches of land, dark, jagged shapes breaking through the shimmer of the seas. Those proto-continents clustered and drifted, sometimes merging into supercontinents before splitting apart again. Names like Valbara, and Kenorland would one day be given to these ancient land masses, though back then they were nameless, anonymous pieces of the world's skeleton. Each one carried its own history of eruptions, quakes, and transformations. The continents also changed the way Earth worked as a whole. They became the regulators of its climate, the guardians of its chemistry, When rain fell on granite and basalt, it reacted with the minerals inside, pulling carbon dioxide out of the air and locking it into stone. This slow, steady weathering acted as a planetary thermostat, keeping the climate from spiraling into extremes. The continents, in their quiet way, made the Earth more stable, not just physically but atmospherically. They were more than land. They were the lungs of the planet. Meanwhile, deep beneath the surface, plate tectonics continued its ceaseless grind. Subduction zones, those fiery scars where one plate slipped beneath another, recycled old crust into the mantle and forged new magma that would one day rise again. In this endless cycle of creation and destruction, the continents were constantly renewed. Mountains rose, crumbled and rose again. Volcanic arcs stitched new land to old. The earth was never still, but it had found a balance, a slow rhythm of birth and erosion that could last for billions of years. Volcanoes, as ever, were the storytellers of this age. They roared and rumbled, spraying molten rock into the sky, blanketing the land in ash. But unlike the early days, these eruptions now built instead of destroyed lava, cooled to form solid crust, and volcanic gases enriched the atmosphere with carbon and nitrogen. Ash, when mixed with rain, became the earliest version of fertile soil, a strange irony that the planet's most violent acts gave rise to the conditions of growth. If you were to walk across one of these newborn continents, impossible of course, since you'd be vaporized, it would feel like stepping through the aftermath of creation. Black rock still steaming, valleys of mineral mud, rivers cutting fresh paths toward young seed. And yet, despite the chaos, something delicate was emerging. The continents, through their endless erosion, were feeding the oceans with nutrients, iron, phosphorus and silica that would soon nourish the first stirrings of life. Though life itself had not yet taken firm hold, the stage was being set. The ingredients were there: solid ground, steady climate, balanced chemistry, and an ocean rich in possibility. Earth was finally providing a stable platform on which biology could dare to stand. The birth of stable continents also gave the planet texture. The rough, uneven surfaces of land and sea created gradients, differences in temperature, salinity, and pressure that drove winds and currents. Weather systems formed, distributing heat and water around the globe. Lightning flashed in growing storms, sparking new chemical reactions in the air and on the ground. The interplay of land and sky, mountain and ocean, became the symphony of Earth's adolescence. It was messy, thunderous, and beautiful. Through all of this, the continents grew bolder, their granitic hearts thickened, their edges cracked and folded into mountains. Some regions cooled enough to form true crustal roots, thick, buoyant masses that anchored them deep into the mantle. These cratons, as geologists call them, would become the most ancient and enduring pieces of the planet, surviving for billions of years. Even today, parts of those first continental cores still lie beneath modern Africa, Australia and Canada. They are the Earth's memory made stone, silent witnesses to a time when the world was learning how to stand still. Erosion, meanwhile, never stopped its patient sculpting. Mountains, no matter how mighty, yielded to rain and wind. Rivers carried their remains to the coasts, where sediments piled up in vast layers. Over time, these sediments hardened into new rocks: sandstone, shale, limestone, recording each age in delicate strata. Every grain of sand was a story, a piece of mountain, a fragment of volcano, a whisper of transformation. And as those sediments accumulated, the continents became more hospitable. Valleys filled with fine clays, plains grew wide and smooth, and minerals leached from stone created pockets of chemical richness. The continents, once barren wastelands of rock, began to carry the potential for fertility. It was as though the planet, having spent eons in fire, was now beginning to practice gentleness. If you could have seen Earth then, you might have mistaken it for a work in progress, half-finished but already magnificent. Volcanoes dotted the landscape like candle flames. Rivers glistened in the dawn light, carving canyons through black and red stone. The air shimmered with dust and steam, and in the quiet corners where water pooled and minerals gathered, there were hints of what was to come, chemical whispers that would soon give rise to the first living things. But for now, the continent stood alone, raw, proud and patient. Their formation was not just a geological event, it was a transformation of identity. The Earth had gone from a fluid, restless world to one with structure and permanence. The continents became the planet's memory, its architecture, its stage. They would drift and collide, break apart and reform countless times over the eons, but their essence, the idea of land, would endure. This was the planet's first true moment of composure. The fiery tempers of youth were gone. The tantrums of impacts had faded. The oceans, now calm enough to cradle reflection, lapped gently at the edges of newborn shore. The continents, heavy with promise, rose like ancient gods from the sea, declaring, "Here, build, stay." They were, in every sense, the foundation for what came next. Upon their backs, life would soon take its first foothold. Bacteria clinging to minerals, mats of microbes spreading across tidal flats, the slow breath of evolution beginning. But even before life arrived, the continents were alive in their own way. They moved, they grew, they eroded, and they began to tell time through stone. In those grand, slow ages, the earth was writing its prologue in granite and basalt. Every mountain was a paragraph, every river, a sentence, every grain of sand, a word. The continents were the pages on which the story of life would soon unfold. And perhaps, if the planet could look upon itself then, it might have smiled, a long, slow smile of recognition. After so much fire and fury, after ages of molten seas and shattered skies, it had finally done it. It had built something lasting, something that could stand the test of time, something solid enough to host the miracle to come. The continents, strong and silent, were the Earth's gift to the future. They were the steady shoulders upon which all life would climb, and though they would drift apart and crash together again countless times in the aeons ahead, their first emergence marked the beginning of everything that matters. The Earth had found its balance. The land had risen. The world, for the first time, had a place to stand. About 3.8 billion years ago, in a world that had finally calmed its cosmic tantrums, something extraordinary happened. On a planet of cooling rock and neutral seas, life appeared. It didn't arrive with fanfare or lightning bolts, nor did it descend from the stars in glittering ships. It emerged quietly, invisibly, small, simple, and yet utterly revolutionary. In a universe still young and chaotic, Earth took a breath and whispered, "Let's begin." It's hard to overstate how unlikely it was. The oceans of that time were vast chemical cauldrons, their waters rich with minerals and molecules drifting aimlessly, waiting for anything to click into place. The planet's chemistry had been simmering for hundreds of millions of years, stirred by volcanic heat, jolted by lightning, mixed by tides. In those warm, neutral waters, carbon compounds danced with nitrogen, sulfur, and phosphorus. The ingredients of life were all there, scattered like letters in a cosmic alphabet. And one day, somehow they spelled the word alive. No one knows exactly where it happened. Maybe it began near deep-sea hydrothermal vents, where superheated water and minerals gushed from the Earth's crust, creating pockets of rich chemistry. Or perhaps it began in shallow tidal pools, warmed by the sun, where evaporation concentrated molecules until they could no longer ignore each other. Some scientists even imagine it started inside tiny mineral bubbles, where natural membranes offered shelter from the chaos outside. Wherever it was, the recipe came together: energy, water, and time. The result was the first cell, a membrane-bound bubble capable of holding itself together and making copies. It was astonishingly small. If you could somehow hold one of those first cells in your hand, you wouldn't see it at all. You'd be holding a ghost of chemistry, a pattern of molecules so simple it could have been mistaken for a trick. But it wasn't a trick. It was persistence. The first life wasn't smart or fast or even efficient. It was patient. It divided, it consumed, it adapted. It discovered the art of staying. In those early oceans, life was a microscopic drama. Billions of tiny players drifting through water, feeding on minerals, light or chemical gradients. There were no predators, no prey, no plants or animals. Just an ocean filled with single-celled optimism. These primitive bacteria and archaea were Earth's first citizens, invisible architects who would soon reshape everything. They ate the planet's chemistry, and in return released new gases into the air and new compounds into the sea. Slowly, molecule by molecule, they began to rewrite the planet. Among these pioneers were the ancestors of what we now call cyanobacteria, tiny blue-green microbes that discovered a trick so brilliant it would change the course of all existence: photosynthesis. They learned how to use sunlight as food. With a dash of carbon dioxide, a splash of water, and a beam of sunlight, they created energy and, almost as an afterthought, released oxygen. It was the greatest side effect in history. At first, that oxygen had nowhere to go. It reacted instantly with iron and other elements in the ocean, turning them into rust. The seas changed color, their greenish hue deepening into a reddish-brown tint as iron oxides rained down to the seafloor. These layers would one day become the planet's great banded iron formations, ancient records of a world learning to breathe. But the bacteria didn't stop. They kept photosynthesizing, filling the oceans with oxygen until even the rocks could hold no more. Eventually, the oxygen began to spill into the atmosphere. For the first time in Earth's long, fiery history, the air carried the promise of breath. It was a slow revolution, millions of years in the making, but its impact was monumental. The planet's chemistry changed, the climate shifted, and entirely new possibilities emerged. The very thing that modern life depends on was, at first, a pollutant. Oxygen was toxic to most of the microbes that had evolved in a world without it. For many, this new atmosphere was the end, but for others, the adaptable, the clever, the lucky, it was the greatest opportunity in history. This moment, sometimes called the dawn of the Great Oxygenation, marked the first time life began to shape its environment on a global scale. The Earth was no longer just a passive backdrop. It was a living, breathing system, transformed by its own inhabitants. The bacteria that produced oxygen didn't know it, of course. They were just doing what worked, but their actions paved the way for everything that would follow. Complex cells, plants, animals, and eventually us. Imagine that ocean now. 3.5 billion years ago, sunlight filters through shallow waters, glimmering on mats of microbes clinging to rocks. Each tiny cell is a masterpiece of survival, absorbing light, dividing, dying, and returning its minerals to the sea. From above, the planet looks different too, still mostly blue but with hints of rust where oxygen reacts with iron. The sky, once thick and orange with methane, begins to pale toward blue. The air is still unbreathable, but it is changing. The stage is being reset for the grand play of evolution, and the main actors, still bacteria, they ruled this world utterly and without competition. They were chemists, engineers, and terraformers, all in one. Some thrived in light, others in darkness. Some lived off sulfur and iron, deep below the ocean floor. Others floated near the surface, basking in sunlight. They invented countless strategies to survive, sharing genes, building communities, and even forming colonies that could move together. If there was a rule book for survival, they wrote it. It's funny to think that, even today, bacteria remain the planet's dominant form of life, by number, by mass, by endurance. Everything else, plants, animals, fungi, are just elaborations on their work, side projects in the grand bacterial experiment. The first cells set the template: metabolism, replication, adaptability. Once those three ideas existed, evolution had all the tools it needed to paint every other form of life that would ever exist. Back in those early seas, though, things were still fragile. Life had to endure constant volcanic eruptions, ultraviolet radiation from a thin atmosphere, and shifting climates. Yet, against all odds, it persisted. The Earth had finally cooled enough for long-term stability. No more catastrophic bombardments, no more boiling oceans. The chemistry of the planet had reached a delicate balance, and within that balance, life dug in. Microbes began to form layered colonies called stromatolites, structures that still exist today in places like Shark Bay, Australia. These were microbial cities built by generations of bacteria that trapped sediment and secreted sticky films to hold themselves in place. Over time, they grew into dome-shaped mounds, rising slowly from the seafloor. Each layer recorded the daily rhythm of sunlight and shadow, growth and rest. To the naked eye, they looked like rocks, but inside they pulsed with living color. Tiny architects stacking life upon life, turning chemistry into permanence. Through this slow work, the Earth itself began to take on a new character. The balance of gases in the air shifted towards something stable. The temperature, once extreme, began to moderate. The oceans grew clearer. It was as if the planet, after eons of turmoil, had entered a kind of partnership with life. The microbes shaped their world, and the world in turn protected them. Photosynthesis was the great engine driving this transformation. With each sunrise, the microbes turned light into food, releasing oxygen that built up in the atmosphere. Over time, this steady trickle became a flow of oxygen, combined with ultraviolet light, to form ozone, creating a protective shield high above the planet. The Earth now had a sky that could block deadly radiation, a small but crucial step toward the possibility of complex life on land. The bacteria themselves adapted too. Some evolved to tolerate oxygen, turning it from poison to power. They learned to use it in respiration, a much more efficient way of generating energy than the ancient anaerobic methods. This innovation allowed them to grow faster, diversify, and colonize new environments. It was, in essence, the discovery of fire, but inside us. And so, the planet began to hum with subtle energy. Chemical reactions cascaded through the oceans like music. Iron rusted, gases mixed, light refracted through clear waters. Life spread, not in leaps, but in ripples. Each new species of microbe added to the world's complexity. New colors, new chemistries, new possibilities. Evolution was no longer just random chemistry. It had rhythm, pattern, direction. If you could stand at the edge of one of those ancient seas, the world would feel both alien and familiar. You'd see no plants, no animals, just endless water and bare rock. But you'd feel the pulse of something alive beneath it all. The faint green shimmer of microbial mats, the glint of sunlight reflecting off a living film, the soft burble of gases rising from the deep. All signs that the Earth had crossed an invisible threshold. It was no longer just a planet. It was a biosphere. And yet, the first life was humble. No brains, no bones, no beauty by human standards. Just persistence. But that persistence was everything. Life didn't need to be large to be powerful. It only needed to endure. Those microscopic pioneers survived through extremes that would kill most modern organisms. Heat, acidity, radiation, and cold. They found a way to adapt to everything, to use every niche, to recycle every resource. They were the masters of resilience, the original survivors. Over millions of years, evolution continued its slow dance. The early microbes diversified into thousands of forms, some relying on sunlight, others on chemical energy from volcanic events. Communities formed, interacting and exchanging molecules. Cooperation, competition, and symbiosis all appeared, long before any animal or plant. The web of life had begun to weave itself. From this microbial foundation, complexity would one day emerge, cells combining into more elaborate structures, forming the first eukaryotes, then multicellular organisms, then everything from jellyfish to humans. But all of it traces back to those first simple cells in the calm, neutral oceans of 3.8 billion years ago. They were the true heroes of Earth's story, the unsung inventors of breath, balance, and persistence. If Earth could speak of that time, perhaps it would smile and say, they were small, but they were mighty. The first life didn't roar, it whispered. It didn't conquer, it collaborated. And in doing so, it transformed the planet forever. So, the next time you look at a drop of seawater shimmering in the sun, remember that it's not just water, it's history. It's chemistry that learned to hope. Every wave carries echoes of those first microbes. Every breeze carries oxygen made by their descendants. We are quite literally breathing their legacy. The appearance of life was not a miracle. It was persistence rewarded. A patient world finally found its rhythm, and a patient chemistry finally found its spark. And from that spark came everything. Forests, oceans, mines, dreams. All of it began with a whisper from the deep, a single cell floating in the warm cradle of a newborn sea, saying to the universe, I am. If we could watch the Earth's story unfold from the beginning, if we could stand above time and see every molten wave, every burst of lightning, every crash of rock from the heavens, we might be humbled by one thing above all else: this planet's talent for endurance. It wasn't born gentle, nor was it crafted for comfort. It began as chaos incarnate, molten, poisonous, and bombarded from every direction. Yet here it stands, billions of years later, a world that learned how to balance, to breathe, to host life, and to keep on spinning. Somewhere in that long arc from fire to forest lies a profound truth. Earth's genius isn't perfection, it's adaptation. When it was young, the Earth was not so much a planet as a furnace wrapped in gas. Its surface bubbled with magma, its air hissed with toxins. You could call it hellish, but even hells can evolve. From that inferno, through sheer patience and persistence, the planet transformed itself. The same forces that once burned it later cooled it. The same chemistry that once killed would someday nourish. It is a reminder that change, though slow and brutal, is the most natural thing in the universe. The Earth, like an ancient sage, learned not to resist chaos, but to absorb it, reshape it, and quietly move forward. Every stage of the planet's early history tells the same story in a different voice. The acidic oceans that could dissolve stone eventually mellowed into the blue expanses we know today. The skies that once choked with methane and carbon dioxide gradually cleared to reveal sunlight and oxygen. Even the endless rain of meteorites, the cosmic tantrum that once erased every new beginning, finally ended, leaving peace in its wake. It's as if the Earth went through every possible trial just to prove one point: that stability is not a gift, but an achievement. Think of the patience that took. The Earth didn't rush its recovery. There was no instant miracle, no overnight transformation. It took hundreds of millions of years just for the surface to cool, another billion for the atmosphere to settle, and still more for the oceans to balance their chemistry. If we, with our human impatience, could learn anything from our planet, it might be this: true change is glacial. It happens molecule by molecule, moment by moment, until one day you look around and realize the world has become something entirely new. What's astonishing is how the Earth turned adversity into opportunity. Every catastrophe was also a classroom. The bombardment of meteorites that seemed purely destructive delivered essential elements: iron, water, carbon, that would later build everything living. The acidic seas that seemed inhospitable helped dissolve minerals, enriching the ocean with the raw materials of chemistry. Even the atmosphere's early poisons, thick with greenhouse gases, kept the young planet warm enough for water to stay liquid. Earth never rejected its challenges. It integrated them. It found harmony, not by avoiding difficulty, but by metabolizing it. You could almost imagine the Earth as a wise old teacher, murmuring through its shifting continents and slow volcanoes: "Change is not an enemy. It's my method." The planet's resilience came from this endless cycle of destruction and renewal. Every impact, every eruption, every storm was both an ending and a beginning. When mountains were worn away by rain, their dust seeded new soil. When volcanoes choked the skies with ash, the minerals they spewed fertilized the ground. When oceans turned acidic, the rocks beneath them worked silently to neutralize their sting. There was no moment of surrender, no tomb. Even at its worst, the Earth kept recalibrating, always searching for a new equilibrium. And perhaps that's the greatest lesson it offers. Survival isn't about strength, it's about flexibility. The Earth did not outlast fire and ice because it was invincible, but because it could bend without breaking. Its crust cracked, shifted, and remade itself. Its atmosphere changed composition again and again, finding balance through constant motion. It was, and still is, a living paradox: steady because it moves, enduring because it changes. There's something profoundly comforting in that. We tend to think of peace as the absence of turmoil, but Earth teaches us that peace is the ability to continue through turmoil. The planet's calm was born from billions of years of chaos. Its stability wasn't inherited. It was earned, crafted from failure and fire. If it could speak, it might laugh softly and say, "You can't skip the hard parts. They're the parts that teach you how to stay." Of course, the Earth had no intentional plan. It's just chemistry and physics, doing what they do best. Yet, Through those indifferent laws, a kind of wisdom emerges. Look closely, and you'll see that the same processes that carved mountains also smoothed valleys. The same tectonic shifts that caused earthquakes also built continents. The same solar radiation that once scorched the surface later powered photosynthesis. Everything destructive carried within it the potential for creation. The universe doesn't waste energy, it repurposes it. The early Earth was a harsh teacher, but it taught in the only language it knew, transformation through pressure. Each trial refined the planet, teaching it new ways to regulate itself. The carbon cycle, the rock cycle, the water cycle, all of them are lessons learned from catastrophe. When the air became too thick with carbon dioxide, the rocks learned to pull it in. When the crust grew too hot, the planet found ways to vent its heat through volcanoes. When impacts threatened to strip away the atmosphere, gravity held tight. These were not perfect solutions, but they were adaptive ones, shaped by the long patience of trial and error. In this sense, Earth is not just a world, it's an autobiography of adaptation. Every layer of rock is a paragraph about resilience. Every mineral deposit, every ancient shoreline, every fossilized ripple of water tells the story of a planet that kept rewriting itself until it found balance. Even today, beneath our feet, it continues. Plates move, volcanoes breathe, the magnetic field shifts. The Earth is still editing its own story. And here's where the humor comes in, because in its long, slow way, the Earth seems almost human in its stubbornness. It doesn't always make the quickest or cleanest choices. It tries something, fails spectacularly, then tries again. It's a planet that learns through mistakes, sometimes dramatic ones. It overheats, then cools too much. It drowns itself in oceans, then freezes those oceans over. But each mistake moves it closer to balance. If Earth had a motto, it might be progress through persistence and a few billion years of trial runs. We like to think of the early Earth as alien, a place utterly unlike our modern world. But the truth is that its lessons are timeless. Even now, our planet continues to adapt to shifting climates, shifting continents, shifting conditions we ourselves have created. The same slow patience that turned acid seas to neutral waters and poisonous air to breathable sky still hums beneath everything. The Earth doesn't resist change, it incorporates it, metabolizes it, turns it into part of the story. It's a humbling perspective, especially for a species that measures progress in election cycles and fiscal quarters. The Earth's clock doesn't tick in seconds, it ticks in epochs. Where we see crisis, it sees process, the extinction of a species, the rise of a new one, the freezing of an ocean, the growth of a continent. Each is just another page in a story that never stops being written. But the lesson isn't to be passive. The Earth doesn't simply sit and wait for things to improve. It acts, it erupts, it shifts, it reacts. Its adaptability isn't a quiet resignation. It's an active, relentless search for equilibrium. The rocks move, the air breathes, the water cycles, all endlessly adjusting, endlessly responding. That perhaps is the most profound wisdom of all. Resilience isn't sitting still, it's moving intelligently. From this cosmic patience, a kind of humor emerges. Picture the planet at its most volatile: magma seas, acid rain, meteor showers, and imagine it saying, "Don't worry, I'll fix it. Give me 1 billion years." It's absurd and wonderful at the same time. The Earth never rushed, never panicked. It simply kept experimenting until it worked. If there's a model for endurance, that's it. In a way, Earth's evolution is less a story of triumph than of acceptance. The planet didn't fight against its nature, it worked with it. It let the heat escape through volcanoes, let the rains fall, let the rocks erode. It allowed destruction to play its part, knowing that every act of breaking also creates space for renewal. What looked like suffering was simply transformation, and perhaps that's the deepest lesson buried in those billions of years of change. Balance is not the absence of chaos, but the coexistence of it. The Earth doesn't eliminate extremes, it finds rhythm in them: hot and cold, wet and dry, creation and destruction. They're not opposites, but partners, dancing endlessly through time. From that dance came continents, oceans, and eventually the thin blue skin of atmosphere that we now call home. If we were to translate the planet's story into human terms, it would sound like this. Endure, adapt, laugh at the chaos when you can. Don't fear change, learn from it. The things that seem catastrophic today may be the soil of stability tomorrow. The acid sea becomes the gentle ocean. The toxic air becomes breath. The fire becomes warmth. The earth has had its share of disasters, yet here it is, still spinning, still shining, still experimenting with balance. Its story is not one of fragility, but of resilience, so vast that it can afford to start over again and again. Every scar on its surface is not a failure, but a lesson learned. Every layer of rock is a memory of persistence. So the next time you feel overwhelmed by the pace of change, by the sense that the world is unstable or chaotic, remember this: our planet once glowed red with magma, rained acid, and was bombarded by mountains from space. And yet, it adapted. It cooled, balanced, and began again. If a world can turn from inferno to paradise, perhaps patience is the most powerful force in the universe. Earth's early years remind us that nothing worth keeping is ever built quickly, and nothing truly resilient stays the same. Change is not a failure, it's the heartbeat of existence. The planet's long evolution whispers a message that echoes through stone and sky. Keep going, you're not broken, you're becoming. And now, we've reached the quiet end of our long journey, the soft exhale after eons of fire, chaos, and transformation. The Earth, once a molten inferno, has become a calm, breathing world. A planet that once hissed and burned and boiled has learned gentleness. The seas that stung with acid now cradle life. The skies that once choked with poison now shimmer blue. The continents, once restless and newborn, now stand strong and patient beneath the clouds. From that long, perilous story of change came the world we know, the tamed earth, the home of life. It's almost unbelievable, isn't it? To think that this soft green planet we walk upon was once so utterly uninhabitable. There were times when no ocean could last, when no breath could be taken, when every inch of surface glowed with molten rage. Yet somehow, through patience and physics, through time and trial, the earth turned its fury into balance. It took its storms and made them into rivers. It took its fire and made it into warmth. And somewhere along the way, in the quiet spaces between catastrophe and calm, it created room for life to begin. This is the story of a world that refused to stay cruel, a planet that adapted, that learned, that softened its edges until it became the nurturing sphere that carries us all. It didn't happen quickly, and it wasn't easy. Every drop of water, every breath of air, every grain of soil was earned through transformation. The earth didn't simply exist. It evolved. It tamed itself. It learned to hold life gently, the way a parent learns to cradle a child. When you look up at the night sky, the stars shimmer like possibilities, other worlds, other beginnings. Some of them may still be in their fiery youth, wrapped in the chaos we once knew. Others might already be calm, oceans gleaming, continents steady. But here on this one world, we can trace the whole story from start to present. From fire or water, from poison to breath, from silence to song. Our Earth began as an alien place. A world not meant for us, not meant for life at all. And yet, by its own slow grace, it became the rarest thing in the universe, a home. Maybe that's the quiet lesson the planet has been whispering for billions of years. That gentleness is born from hardship. That balance is the child of chaos. That life, to exist, must first survive the storm. The Earth's taming was not a single event. It was a long act of becoming, a cosmic meditation in patience, persistence, and adaptation. So now, as you rest beneath this same ancient sky, take a moment to breathe in what the planet has made for you. The oxygen that fills your lungs was once a dream in the heart of a microbe. The water that cools your skin once steamed from the mantle of a molten world. Every breath, every heartbeat, every quiet moment of comfort, these are gifts forged from ancient chaos. The earth has tamed itself, but it has not stopped changing. Even now it continues to evolve, slowly, gracefully, endlessly. Its story is not over. It simply turns another page, carrying us along with it. So, as you close your eyes tonight, imagine that long, incredible journey. The fire, the oceans, the rust-red skies turning blue. Imagine the earth learning how to be kind, and in that calm image, may you find rest. From inferno to paradise, from storm to stillness, the earth has become a cradle for life. What began as a hostile planet now hums softly with the breath of everything that lives. It is, at last, home. Thank you for traveling through deep time tonight. If you enjoyed this journey, share your thoughts. Let curiosity keep glowing within you. And as always, sleep well beneath the patient, dreaming earth.